Hello, everybody. My name is Andrea Malchiodi, and I'm the current director of the Georgi Mathematical Research Center. I would like to welcome you to this meeting, Women in Dynamical Systems and Ergodic Theory. I will just say a few words about the Georgi Center, and promise I won't take much of your time. So the center was founded about 20 years ago, formally as a research laboratory of Scuola Normale Superiore, but with a mission of being like an aggregation center for the whole mathematical community in Pisa, which also includes many colleagues from the University of Pisa and a small community from Scuola Superiore Sant'Anna. And these two institutions, especially the former, contribute financially and crucially to the activities of the center. So since the foundation, the activities of the center have been workshops, intensive research periods, research in pairs, and we started also recently a colloquium series. We also have two types of visiting positions, short-term visiting positions to run research in pairs or groups, and also 2 years postdoctoral positions, typically with an yearly opening. Basically, that's all I wanted to say, and I just would like to conclude by thanking the organizers for bringing up this really nice event, and also the staff of the center for their constant and very valuable support. Thank you.
So thank you, Professor Malchiodi, and welcome everyone. So I will start by quickly thanking our sponsors. We would like to thank Centro di George, Scuola Normale Superiore, UniCredit Bank, Department of Mathematics, University of Pisa, and Project Print 2022 Stochastic Properties of Dynamical Systems, and University of Zurich, Switzerland, for their generous financial support to host this event. Further, I would like to thank our wonderful team from Centro di George, and special thanks to Monica, Federica, and Giuseppe for going above and beyond to make this event possible. So thank you very much. Monica is not present here, but Giuseppe and Federica are there, so we should have clap for them. Also, I would like to thank our IT support team and SNS Media and Communication team and everyone who is working beyond the scene. Further, we would like to thank our scientific committee, all speakers, and my other co-organizer, Carlo and Tania, for their valuable help. So now let's invite our first speaker. It's our pleasure to have Michela Procesi from University of Rome 3, and she will speak about KM theory in infinite dimension. Thank you.
Thank you. This should start working. Can people hear me? Well, I think people could hear me even without the microphone, but I'll keep it. So I'm very glad to be here. I thought that I should try to give a less technical presentation, and hopefully I will be able to do that, but stop me at any time. I mostly work in small divisor problems for PDEs, and I thought that that was not really the perfect subject for this audience. So what I want to show is a model instead on lattice systems. And it's work that I did in collaboration with Guido Gentile and Livia Corsi. And it was for, you can find the relevant preprint on archive, and it was for a volume on 70 years of KM theory. So the idea was to choose a simple model. So what is my point? I am going to consider the simplest model that is dealt with in KM, so Kolmogorov-Arnold-Moser theory, which is a close to integrable system made like this. Well, I have a 1/2. J goes from 1 to some capital N plus a perturbation. So these are actions, these are angles. In a finite dimension, and epsilon is supposed to be small. So at epsilon equal to 0, The dynamics is, of course, I of t equal I of 0. And the theta of t is I of 0 times t plus theta of 0. Okay? And so all the motions are on Tori, and the frequency is given by the actions. So the question that is, then this is, let me say, this is the simplest possible model of this form. And if you don't like Hamiltonian systems, you can think it as a second order problem. So this is, I will get the sign wrong. Theta j 2 dot is equal to minus epsilon, the derivative with respect to theta j of the potential. So the question is, if epsilon is equal to 0, I know perfectly well what are all the solutions. And if epsilon is small, what of the linear problem persists in the nonlinearity? And the answer by KM theory is that many of these solutions survive. So many invariant Tori survive. For epsilon different from 0. Many being in the sense of measure. But the point, and I'm going to show you, at least try to give you an idea of why this is so, is that the Tori which survive, is it clear? This spans a torus, but I will show it a bit more clearly. So the solutions that survive, the linear solutions that survive, are the ones in which the frequency satisfies some non-resonance condition. And usually the condition is a Bruno condition, or you can think of a Diophantine condition. Okay? So what is the kind of solution that I look for? And when I say I'm looking for an invariant torus, of course, since this is a second order system, I just need to give the equation for theta, but I will write both. So for me, an invariant torus is something like this. Theta of t is just omega times t. This is the frequency. Plus some quasi-periodic function, so a function of n angles, computed at, and here I can put an epsilon. So you see that, and well, theta of 0. I am ignoring this, okay? And you see that if you put epsilon equal to 0, this is just this solution here. And then I of t will just be the derivative of theta of t. And u will be a function from an n-dimensional torus into. So this is a function which is periodic in all its variables. This is the kind of solutions that survive, and I'm saying that they survive. So they are there if epsilon is small and omega is non-resonance. So this is a perfectly well-established theorem known since 70 years, more or less. But, and what will be my point? My point is that usually in these theorems, it is very important that the dimension is finite. Because usually, as you send n to infinity, the smallness condition goes to 0. And it goes to 0 very badly. Yes? I'm keeping it vague. It will be, so I will give the Bruno condition, but usually if you know the Diophantine is fine. But I will give you I'm just trying to keep it vague now to give you the setting. So as I was saying, the problem is that it's as n goes to infinity, this goes to 0. And it goes to 0 very badly, like 1 divided by n factorial. And so you could think this is hopeless. But the point is, can I give some conditions? And I'm going to give some conditions on this function here in such a way that I can pass to the limit without sending epsilon to 0. So that will be my game. And before I go into the question, Why is it interesting? Well, for me at least. I mean, of course, it's a question one could say poses itself, because having information which is uniform in the dimension is nice per se. But, and in fact, people worked on this kind of questions since the 80s, just trying to understand lattice systems. For me, the interest came from PDEs. And because in many PDEs, you can think that your PDE is just a lattice problem, an infinite lattice, because you take your PDE and maybe pass to Fourier coefficients. And then there is, so this is what I'm working on mostly, and most of the questions about the persistence of these solutions are open. So for me, it was an interesting, and this is, in some way, it captures the difficulties, but leaves out many technical questions that appear in PDs. So let me try to give you an idea, and then I'll push this blackboard above, of why do you need the non-resonant conditions, and what are the kind of problems that you have in these questions? So, of course, I mean, this, you have an equation with a small parameter, you have your supposed solution. Of course, here, this again depends on epsilon. You might think, let's try to prove that this solution is analytic in epsilon and plug it inside the equation and try to solve by perturbation theory. And in fact, you can do it, but it's not at all simple, because you will have small divisors. It's not like implicit function theorem problem. It's highly singular. But if you plug this inside the equation, so I'm just going to take this and plug it in here, you get, so omega dot phi squared applied to u. So the second derivative of capital U will be equal to the epsilon erases. And here I have the derivative with respect to theta j of f computed at omega t plus epsilon. So I'm calling this the angle instead of putting omega t. Okay? And then imagine that you want to solve at first order. What do you get? Well, at first order, I'm just putting this epsilon equal to 0. And so I get omega dot phi squared capital U is equal to the theta j of f computed in the angle. Okay? I don't have room, so I have to pass. I write too big. I know it, but I'll never learn to do it better. So now imagine that you just pass to Fourier coefficients. I forgot to say, but you need to assume that S is F is very regular. And in my case, I will always assume that F is analytic, because it's the simplest possible case. So just write F in Fourier. And since I have n angles, I will be working in an n-dimensional lattice. Try to, in these things, you can always imagine I'm trying to push to infinity. So keep track of the capital N's. So it's something like this. Well, L dot phi. So this is just Fourier series. And these are the Fourier coefficients. And the Fourier lattice is Z to the dimension. Okay? As many angles, as many as the angles. And then you can do the same for capital U. And what is the equation? Well, if you plug this inside that equation, you will get that omega dot L squared UL is equal to FL. And this equation becomes completely trivial to solve on the Fourier side. But the point is that UL will have, sorry, IL FL. So this becomes a trivial algebraic equation, which you can solve directly. The point is that in order to solve it, you need that this is not 0, otherwise you have a proper kernel. And in any case, you cannot expect that this scalar product, this is just a scalar product between the lattice and the frequency on which I have the torus. And what you should expect is that you need some lower bounds on this, because it goes on the denominator. Okay? So not only it should not be 0, I need some bounds. And this is where the non-resonance conditions come out. So you see, just imagine I'm saying that F is analytic. Analytic means that this goes like some constants times, this might be the L1 norm, okay, the sum of the components. So you need that this omega dot L is at least bounded away from 0 by something like this, because you need to have some analyticity. So this kind of thing is necessary. But it's quite clear that it's not sufficient, because you have to, in your perturbation theory, assuming even that if you even have a hope of convergence, you need to do this infinitely many times. So you will need a better condition. And what is usually opposed, and what I'm more familiar with, is the Diophantine condition, which looks like this. And you see, this is a very nice condition, because in this condition, this term here will contribute an L to the 2 tau, which is compensated by exponential factor. Okay? And this is something that you can repeat. If you have this condition there, what I need is, so let me be clear, is something like this. This will be some e to the minus s L times L to the 2 tau. Okay? And you see, this is uniformly bounded. It's clear that this I can control, because this is a polynomial factor and an exponential factor. Not only, I can do this as many times as I want. I can do this by losing very little analyticity. So at the end, I'm not going to try to prove it to you, because I actually probably would not be able to perfectly do the proof. But let me just write to you what is the kind of condition that you need to close the scheme. So you need what is called the Bruno condition. With a J or a Y there, depending on who you ask. And it's like this. So remember, your point is that you want to control factors like this, and you might have, for just one numerator, many denominators of this type. So at the end, what you get is that you do it by some scales. So you introduce a function. I'm using the notation that I learned from Guido and Livia, which you can find other ones, but please don't ask me too much about this, because I took them from them. There are other versions, except that I'm ignorant of them. So you take the infimum of the divisor over some fixed R. This should be a large number. And then what you're asking is that the sum to the minus n logarithm of 1 divided by beta 2 to the n will be smaller than infinity. And this is the kind of condition that you need in order to prove the convergence. And in fact, if you are in the lowest possible dimension, I think this is also optimal. In other cases, I don't know, but it's a condition. So this is the scheme this is the scheme, this is the condition. And the question is, am I able to pull this to infinite dimension? So I ask myself, okay, so you can safely ignore this. I just wanted to write it once for you. So there is some conditions on the omega. And mind you, here I haven't shown you that this condition is met by a non-empty set of vectors. Of course, this is a non-trivial question, okay? So when is this condition met by some vectors? And the answer is that it is positive measure, actually, full measure. So you should be happy. At least in finite dimension, this is fine. So the question is, when can I pull to infinity? And maybe I will leave that, erase this Bruno condition, and give you the theorem, so that you can get a feeling of what I am trying to do. And then I will try to give you some ideas. I forgot my phone. Is yours? There. No. How does one check the time on that? Okay, maybe I'll get my phone. Sorry. Yeah, but I'm happier if I have a way of checking. So here. So let me consider exactly the same case, but in order to be able to ensure that I can pass to the limit, I'm just directly going to the limit. So I'm going to consider this Hamiltonian system here. And the only problem is that I have to tell you what does it mean that this is an analytic function of infinitely many angles. Infinite angles. Okay? But if you think of it at the second order system level, this is pretty obvious. You just have an infinite chain of second order equations of this type. So you should be happy. The only problem is that it might be that this is infinite, that the energy of a solution is infinite. This I will have to check, and it would be a point. Okay, now, what does it mean here? What I'm saying, well, analytic functions of infinitely many angles are by construction the limit of analytic function of finitely many angles. And what I will ask is a rather strong condition. So I erased it. So I will have to have the Fourier series. Let me write the obvious part, e to the L dot theta. But the point is, in which lattice does this live? So if you were in n dimension, this would be z to the n. So in principle, you would say, okay, here I am taking z to the infinity, which if I assume that the angles, let's say that they are indexed in the natural. So it's theta 1, theta 2. Of course, I could assume whatever I wanted, right? So here you would have z to the naturals. But the point is that this is not necessarily well posed because it's not clear what does this mean if you have an infinite sum and these are integer vectors. So what you ask is that this has a finite support. So this means that L, L1, L sum n, and then 0. Except that I don't have a uniform bound on this n. It can be arbitrarily large, okay? And then everything makes sense. And this is a rather nice way of writing analytic functions on infinitely many variables. So of course, I need some condition to ensure analyticity and even that this makes sense, that this sum makes sense. And because in principle, even trigonometric polynomials are finite, infinite sums in these notations. And my condition, which will be my analyticity condition, looks like this. So I need to control the Fourier coefficients with some exponential decay. So what I'm going to do is that instead of putting the L1 norm, so the sums of the moduli of the component, I am going to introduce some special norm, which will be the whole key of my proposition. And so you see, this against some exponential weight should be convergent. And what is the exponential weight? Well, first I'll write it and then I'll try to explain what it is. The norm L star looks like this. You make the sum. And here, this would be what you would be used to doing in finite dimension. And now I'm going to add a weight. And this weight, well, I am making a rather arbitrary choice in order to give you one theorem. Of course, we have a large number of possible weights. You plug something like this, 1 plus, so 2 plus the absolute value of I cube. So this seems very arbitrary, but I will explain what does this mean and why this is a useful point of view. So you see, I'm putting a much stronger norm with respect to the L1 norm. And of course, this only works because I have only a finite number of non-zero components. Well, this is true also for the L1. So we are fine. And my theorem is if F is analytic, then many solutions survive. And what do I mean by many solutions on Tori survive? It's just exactly those that I write there, except that now omega, so theta is an infinite list. Omega is an infinite vector, because imagine you're just sending n to infinity. And also u, instead of living in R to the n, it lives in an infinite dimensional space. But I mean, formally, I can say exactly the same thing. And then I can actually also specify perfectly clearly function spaces. I mean, it's not a formal statement, okay? And what is the idea of this condition? So a condition of this type says the following thing. So let's imagine that you have your function, and this is the first angle, θ1. And then you have θ2, and then I am not able to go further, but you can imagine that I have infinite limit. So maybe I'll just do θn. Okay? So an analytic function means that you have a complex extension. And the strip of the complex extension is given by this number here. Okay? So something like this says that you can extend your function instead of just being on the real, so you can extend it. This would be complexification of the torus. You can extend on a strip S, okay? And the larger is the strip, the better is the decay in the analyticity. So what I am saying is that you have some analyticity in the first angle. On the second angle, I will have, instead of just having S, I will have S times this factor. So I will have a much larger strip of analyticity. And what I am saying is that the more angles I consider, the more analyticity I ask for, okay? And at the end, so if I'm looking at a very large angle, it will be extremely analytic. And that is the game in order to make the uniform, in order to make the limit n to infinity work. Because if you do not put any condition on the analytic function and just ask yourself, is it true that you can send capital N to infinity? The answer is no. So we knew that you had to put some condition. And there were, in fact, many flavors of conditions. And what I think is nice is that we were able to encode all the conditions in one norm. And of course, you can ask, well, okay, why did you make this choice? Well, you are trying to look for the weakest possible condition. You know that you have to ask a condition in which the analyticity strip of the torus goes to infinity. You are sure that that is so, because otherwise it's quite clear that nothing will work. So you're asking yourself, what is the weakest condition? So how slow can I make this go to infinity? And the answer was anything larger than 2. So what we wanted, because this is a big conjecture in PDEs, what we wanted was to be able to do this with 1 here. Alas, no. We could do it with 2 plus. Well, I mean, 1 is happy with what 1 gets. And so the other nice thing of this approach, and then I'll try to tell you other possible ideas, because so the other nice thing is, what does it mean many solutions survive? Well, in the thing above, in the finite dimension, I could say that the solutions which survived were parametrized with the frequency, which was a vector as many dimensions as the problem. And this frequency had to be Bruno, the condition that I wrote to you. So you would like this to be true also in infinite dimension. And it's true. So I'll put a star here. So I want to find solutions like this. So in order to get a solution of that type with an infinite dimension, omega, which now has to be, it's almost indistinguishable, but these are the naturals. So this is not n, sorry. So this frequency should satisfy some non-resonance conditions. And what do these non-resonant conditions become? So the first thing that I should do is I should try to fix a box, because I would like to give a probability measure, and I would need, I don't like to work on this whole space, because in infinite dimension, it's rather unpleasant putting a measure on this set. It might be not particularly interesting, let me say it like this. So what I'm going to do is I'm going to ask, for instance, that actually we need even a smaller space, but let's say that I take -1, 1 to the naturals. So each coefficient in omega should be between -1 and 1, okay? So, and I want to take a set which has probability measure, positive probability measure in this set, and this will be the good sets. So what is the condition? Well, of course, you have already forgotten the Bruno condition, but the condition is this. I again define a function which tells me, was like this, omega of r, which tells me what is the worst small divisor. So I take the infimum. Here I have the norm of L, which should be smaller than R, different from 0. And here I have the possible small divisor. And what is my only concession to infinite dimension is that I'm going to put here exactly the same norm that I gave for the analyticity. So I'm going to put these weights on the norm. And then my condition becomes exactly the one in finite dimension. Sum 1 divided by 2 to the n, logarithm of 1 beta 2 to the n of omega, smaller than infinity. So what is, at least in my opinion, the nice thing about this kind of results is that I am trying to put all the condition in one simple functional analysis question. So my result is that if the function is analytic in the sense that it is analytic with respect to this norm, and if the frequency is Bruno in the sense that it is Bruno with respect to the exactly same norm, then I have this uniform result with n to infinity. So if you like a finite dimensional result, because you might prefer finite dimension, you can think it exactly in the same way, except that in the angles, you have to assume that your finite but large angles have more and more analyticity. And when you weight the small divisors, you don't weight them uniformly, but in some way, you weight the large, the L corresponding to the frequencies corresponding to large angles more. So provided that you use this rather curious and not particularly intuitive non-uniform norm in bounding in computing your small divisors and in bounding your analytic functions, everything works word by word like in finite dimension, which is nice because this theorem that I told you it's the first finite dimension result that one learns in KM theory. So it takes you to a very straightforward domain. So, and also, this might not be very hard, very easy to transmit, but it is true. So this condition is a condition which has a positive measure inside this set. This is far from trivial, of course, and one of the points that is interesting, provided that here I put what is called the probability product measure, which is nothing particularly fancy, you can imagine that this omega is omega 1, omega n going to infinity. And you can imagine that each of these coefficients is a random variable distributed uniformly between -1 and 1. And these are all independent. And then with a positive probability, you have that this condition is fulfilled. Okay? So it's really the rather natural way of saying many omega of this type fulfill my condition. And also, well, provided that you put a bit fancier condition here, which I'm not going to state because I thought it would not be of any interest, but you can also make it so that my solutions have finite energy, which in this kind of limits is usually a big deal, because usually when you're trying to pass to the limit, by construction, your energy goes to infinity. And instead, we can manage to make it finite energy, which we wanted to. So this is the result. I'm going to try to give you now some ideas of what are other possible approaches so that maybe you can get a feeling of why we like this. So let me go back to my original question. And you can compare finite dimensional with infinite dimension. Okay, so in finite dimension, if you put no conditions in particular, you expect that epsilon should be smaller, well, in modulus, by something which goes like n to the factorial to some power. So if you put no conditions, you cannot expect in any way to go to the limit. So so the first thing that people did was they were interested in lattice systems. So in many lattice systems, you can think that you have a chain of oscillators, and you're only interested in cases in which you just have an interaction between the nearest neighbors. So you can imagine that I have my lattice, and in some way, each f involves theta j and theta j plus 1. Okay, and so you have only connections between the two closest, or maybe to make it symmetric, the two nearest neighbors on the two sides. Okay, and there was a result by Wayne in, I think, 84. And if I understood correctly, it was able to get n to the some power, which is much better, but still does not pass to the limit. Nearest neighbors. Okay? And then there were, in fact, some results that combined analyticity conditions with the nearest neighbors and were able to push this scheme to the infinity, so to get a bound on epsilon, which does not go to 0 with n. But what they needed, I don't remember the name, it was Fröhlich and some other people around the 90s. I don't remember, I think, yes, I think it's that, thanks. I was not sure that it was also with Wayne, but I think, yeah, you're right. So what they were able to do, so you have nearest neighbors. And then you ask that the analyticity, so you remember you have this condition here. They don't write it in this way, but it's written in terms of the actions because they actually have actions here. So it's a rather different technique, but their point will be something like this. If you rewrite it in our language, you can rewrite it like this, except that their norm there, so you see that's exactly my condition. You can rewrite it like this, but their norm there was, if I remember correctly, something like some Li, and then here I have 1 plus modulo of I to, I think, well, 1 plus. So you're missing a logarithm. This goes to infinity much faster, okay? It's not completely trivial to go from their conditions to this one, but I'm convinced that this is the point, okay? So, I mean, it makes, so our condition is actually, well, not only we don't need the nearest neighbors, but we can do also better with the analyticity strips. So, the results I'm more familiar with are without nearest neighbors. Why? Well, because I work in PDEs, and in PDEs you can't do nearest neighbors. So that's why these I know much better. So here, well, you can see results formulated in various ways. The nicest thing, as I found in this paper by Perschel on the 90s, and he also, he started from nearest neighbors, but wanted to go to more general conditions. And the thing that I liked, because it was really, I found it, he's a very precise mathematician, and he says, the trick is you have to take this function f, and you have to think of it not as just one function, but you have to divide it in chunks, which I really liked for the word chunks. So what is the idea? Well, for me, a very reasonable way of seeing this is the following. You still have your piece, so now you're in infinity or finite or whatever you want. And instead of putting just one function, imagine that you have a sum of possibly infinitely many functions made like this, epsilon j, and then I have a function which is function of theta 1 up to theta, maybe I'll call this k, dk. And then I have the sum over k. So for instance, I start with one piece depending on 2 angles and 3 angles and go ahead to infinity. And then some results become essentially completely trivial, because you see that if you make a truncation here, you're just looking at finitely many angles. And so you expect to have a finite dimensional result. So if your epsilon k goes like some small epsilon divided by some power of k factorial, this has to work. It stands to reason. And in fact, this idea was, I mean, it seems you say, well, it's obvious, but this was the idea that made Perschel be able to do the first result for infinite torides in PDs. So at the time, it was a big deal. It was the first result of this type for PDs. Then if you try to push this, so you say, okay, but I mean, of course, I need this to go to 0. Otherwise, this is not even summable. And what am I talking about? But let's try to understand how can I play this game. So can I make less assumptions than these admittedly trivial ones? And then there is this paper by Cheriath, 95. So what was the remark by Cheriath? I think these are the really nice papers, because once somebody tells you what the remark is, you say, it's obvious. But before, nobody had thought about it. So, I mean, What was their idea? Their idea was, let's forget about Bruno condition. Let's think that in order to make a finite dimensional KM scheme, I need to impose a Diophantine condition. So here I have infinitely many. So in order to solve a truncation at K, so I want to solve the Kate problem, which has K angles. Let's just put K here, more and more angles. I mean, it's useless that I make fancier things. So what kind of conditions you have? Well, remember, it's parameterized by the frequency, which, of course, at this point, if I'm only looking at K angles, will be a finite dimensional vector. And the least fancy condition that you should put is a Diophantine condition. And what do Diophantine conditions look like? Well, they look like this. You have a parameter, which in principle might not depend on the dimension, but let's imagine that this numerator depends on the dimension, divided by your denominator, which is a polynomial. So it's just modulo of L to some power. And what should this power be in order for this condition to get a positive measure set of this omega? This is, of course, always the point is, I can put larger than 1, but if I put larger than 1, then I have no omega which satisfies. So, well, you should ask, I think it might be K minus 1, but let me put K, something that goes to infinity with K, okay? This is the kind of condition that you expect to pose if you are working with a K-dimensional vector, and which will ensure that you can solve your problem. So the point was, what can I do with this gamma? Can I send, okay, this goes very badly to infinity, but could I take gamma K going to infinity and still have a positive measure set of omega? Well, if you try to do this with this in a ball, of course not. But if omega K goes to infinity with K, then you can also take gamma K to infinity. Okay? And this becomes nice because this condition here gives you a smallness condition like this. I'm waving my hands, of course, all this has to be proven, but it's something like this. Gamma K squared K factorial to some power. This should be small. Now, I guess you see my point. I can either make epsilon small with K, or I can make gamma large with K. The point is that I have to do this by still keeping a positive measure set. And so what do? You just have to require that this omega go to infinity. And this was the trick by Cheriath Perfetti. Okay, so of course, what is the problem? Well, I did not really show it to you, but if you make the computations, if omega goes to infinity, there is no hope that this is finite energy. So if you're asking yourself, can I do a finite energy result with this method? Absolutely not. But otherwise, this is a splendid idea, I think. Okay? So I think these were the results. So let me see, I have 10 minutes. These were essentially the kinds of results that were available. So we wanted to try to put all these in a unified notion. And why do I say that my result unifies all this? Well, because you can restate it. Maybe at this point you remember the equations. I'll leave this up and right there. So what was our idea? We wanted to encode everything with this norm, which I called the norm star. So we had two definitions: star star analytic, which was the star comes from this norm, which I put on the dual lattice. And then I had star Bruno, which means that when I define my Bruno function, I am doing the infimum of the denominator with this particular norm here, okay? And the result that I gave you was for a particular choice of this star norm. Let me remind you, which was L star, which you can think of as just a weighted L1 norm. And what I gave you was am I supposed to stop in 50 minutes, or did I really have 1 hour? I'm sorry. Okay, sorry. So let me, with Wi, which was this strange logarithm. So, and then I'll close. What was our real result? The first result was for any norm star, if F is star analytic and omega is star Bruno, you have a solution. This holds always, whichever is the norm here. The point is, when is it true that this is an empty set? This depends on where do you want to choose omega. So if omega is living in a finite box, you need this condition here. You only need it to make your result not purely formal. Otherwise, this holds anywhere. And now, if instead of having this condition here, you have the condition of Cheriath perfetti, in which this goes to infinity, actually this goes exponentially fast, super exponentially fast. Well, if you're in this setting, do you need this condition? No, you can take one. And then you get Cheriath perfetti. So you see, I have a formal result, and then my point is I reduce everything to trying to understand when I can impose this Bruno condition. And I find this pretty neat because it reduces everything to one single problem. Of course, I'm not saying that this is a trivial result to prove, but once we understood the idea, is extremely similar to the finite dimensional case, which, as I said, is classic. Okay, so thank you. I'm sorry if I... Well, I think everybody heard. But...
Questions?
This conjecture from PDs where you wanted something to be one, but actually your result. Yeah, can you say more?
Yes, yes, of course. So the question is, yeah, I knew I wouldn't have time, but if I did, I would have liked to say something about this. So you have your nonlinear Schrödinger equation. And to make things a little bit simpler, you add the potential. And to make it even simpler, you add a convolution potential. Plus u squared u equal to 0. And let's consider the Cauchy problem. Small initial data. And X is on a one-dimensional torus, because this is the simplest model for which this question makes sense, okay? So if you did not have the nonlinearity, all my solutions would be exactly the tori that I was discussing, and the Hamiltonian would be, apart from a translation factor, exactly like this. So the question is, what is the minimal regularity for which I can prove the existence of maximal tori? So it's important that I say maximal tori, because otherwise there are a large number of results. So infinite dimensional tori, in which all the actions are positive. And at the moment, the only thing that one can do is if this initial data are at least C infinity, in fact, Gevrey. And one would like to have the existence of this infinite tori even in the case of finite regularity initial data. Mind you, I'm not talking about the regularity of the nonlinearity. I'm talking about the regularity of the initial datum, okay? Now, in a way that it's not trivial to show, this exactly translates, you expect to be able to understand this problem if you can prove exactly what I gave you, but here with logarithm instead of logarithm cube. So if you were able to do this, then we expect to be able to go to this problem here, which is considered one of the big open problems. Of course, the very big open problem would be not to find one solution, but to prove that a positive measure set of initial data have solutions which live on infinite tori, but that's going harder and harder. Okay, thank you.
Thank you.
Any other questions?
Okay.
If not, let's thank the speaker again. Welcome everybody back. And now it's our pleasure to have Lucia Rossi, and she will talk about number system with rational bases and fractal sets.
Thank you very much. Good. So what I'm going to present to you is part of the work that I did on my PhD. So to start with, I'm going to consider an example. There is a classical example, and then I'm going to consider, let's say, a new example, which is a rational example. So let's say, so this is a self-affine set. A self-affine set is a set that is the union of smaller copies of itself. So this is a famous one, which is known as the twin dragon. It was originally discovered by Donald Knuth. So there's more than one way to define this set. I'm going to consider one way which is related to numeration systems or number systems. So for this example, we can consider a complex base that I call alpha, which is -1 plus I, and then a set of digits which are 0 and 1. And the choice for these digits is that they are a residue set of this ring spanned by the base modulo the base. So it's a residue set in the, in the natural sense. And how is the twin dragon defined? It is defined as the solution of a set equation. So it is a set that is contained in the complex plane and satisfies this property. So this set T on the left-hand side, I multiply it by the base, -1 plus I, and on the right-hand side, I consider the union of two copies of T, which are translated by the digits, which are 0 and 1. And one thing that you can note is that here, this complex number, if I compute its norm, its complex norm, it's 2. So a property of the complex norm, it's similar to the determinant of a matrix. So if I multiply a set by this complex number, the new area is actually twice the area of the set. So then I have on the left-hand side something that is twice the area of T, and on the right-hand side, I have 2 copies of T. So that allows that this union is 2 copies with disjoint interiors. And actually, the only overlap is here in the boundary. So the boundary of this set is what makes it a fractal. So this set, because it's self-affine, it gives a tiling of the plane. A tiling means, I can cover the plane, only overlapping in the boundary. And this is a consequence of the self-affinity, because if I have a set that I can subdivide many times, I can also, place it together many times and get a tiling. And then one interesting property is that having this tiling property allows me to have unique expansion of complex numbers in this base. So if I want to expand numbers in this complex base, using these digits, I actually will have an unique expansion almost everywhere, just like happens with the decimal system, for example. And that is a consequence of this tiling property. So as I said, I chose 0, 1 because it's a residue set. And if I have a complex number x, I can write it in this way. So I have powers of the base starting somewhere, and then multiplying by the digits that can be either 0 or 1. And this is unique almost everywhere. So basically, this is like the desired property of a number system, because that means that I have an efficient set of digits. Now I'm going to consider a non-integer example. And first, I'm going to show why this at first seems like it's not working when I want to consider unique expansion. So I'm going to explain the whole talk based on one example to make it simple to understand, but naturally similar ideas can be generalized. But I'm going to consider one example, which is this number, -1 plus 3i over 2. I chose it because of the examples that I looked into. This looked nice and easy, but I could have chosen something else. And then I'm going to consider a digit set, which is 0, 1, 2, 3, 4. And again, this digit set is a complete set of residues of Z of alpha modulo alpha. So let's say that I set up a set equation like before. On the left, I have a set. So I have a set F. On the left, I multiply it by alpha. And on the right, I consider a union of translations of F by these digits. So this is what this looks like. I have a set that is the union of smaller copies of itself, but the copies overlap. So that means that this is not a self-affine set like the one that I had before. So what is the cause of these overlaps? So again, this number is -1 plus 3i over 2. If I compute the norm of this number, this is 5 over 2. So it's a rational number. And that means that if I consider alpha times f, the area of alpha times f is 2.5 times the area of f. However, I have 5 digits, so I have 5 translations. So this union is actually not almost disjoint. So one way to understand it is to say, okay, I actually have too many digits for this base. And because I have too many digits, when I want to expand a complex number, I'm gonna have multiple expansions. And then this multiplicity of expansion, this is visually seen with this overlap situation. So here is like a spoiler. What do we do, or what if we wanted to obtain unique expansion or like solve this issue? Well, this could be done by considering a set that lives in a more general space that has one extra dimension. So what is represented here is the set that I had before, but embedded in a new space. So, and then this vertical dimension will make things work the way I want. So this idea of this new dimension is based on a paper by Steiner and Tuss-Wallner, which is called Rational Self-Affine Tiles. So this was the starting point of, part of what I researched. And then one thing that I did was, well, I obtained more general results that I'm not going to go into details because it's only a short talk. But one thing that I did was to use Gaussian primes to define this space. And then I'm going to show you how this is done. So this number alpha, one would normally express it in this form. However, I wrote it like this, as a quotient of two complex numbers. And why did I choose these two complex numbers in particular to write alpha like this? So because these numbers are actually Gaussian primes, which generalize the notion of usual primes. So we can think of alpha in some way as a rational number, so at the quotient of two primes. So I'm going to explain a little bit about Gaussian primes. So on the one hand, we have the ring of Gaussian integers. This is the complex numbers whose entries are integers. So real and imaginary parts are integers. And then a Gaussian prime is an element of this ring that is not zero and is not a unit, such that when I divide a product, it divides one of the two factors. So it's a more general notion of being a prime. So it turns out that every Gaussian integer has a unique factorization into Gaussian primes, up to maybe multiplying by some units, so maybe the minus sign could be below or things like that, but essentially this is unique. And also Q of I, so these are the complex number with rational entries, is the field of fraction of the ring of Gaussian integers. So also rational numbers, rational Gaussian rationals can be obtained if I allow quotient. So if I allow a denominator, I can obtain all the elements in Q of I. So I'm going to consider one Gaussian prime, which is 1 plus I. This is the one that was in the denominator. So this one, this one, the denominator, and then this field Q of I. So if I take an element X in this field, then I can express it in this way almost uniquely, up to maybe some unit. And these coefficients might be negative. So I will define a space that is like a p-adic space, but in the complex setting. So for that, I'm going to define a valuation, which I call the 1 plus I-adic valuation, which for every number X, it outputs this exponent, which again, it might be negative, of the factor 1 plus I in this decomposition. And I'm going to define an absolute value, which is that the absolute value of X is 2 to the minus the valuation. So this is exactly in the same way that we do for prime numbers. And this number 2 is because the norm of 1 plus I is 2. So using this absolute value, I can define a space that I call K1 plus I, which is the completion of K. So K was Q of I. It's the completion with respect to this absolute value. So this is very similar to the field of two-adic numbers. Yes. So for example, what does this space looks like? So in this space, large powers of 1 plus I, they are small. So for example, this sequence, 1 plus I squared, 1 plus I cubed, this converges to 0 in this space. And then basically the idea is that I'm going to consider a representation space. I mentioned before I was going to add one dimension. This is the dimension that I'm going to add. So I'm going to consider this space, C times K1 plus I. And then it turns out that this space is going to somehow help me get rid of this denominator that I had before that was bothering me when I was trying to get unique expansions. So I'm going to define a set. Again, it's the attractor of a set equation. And it's defined in this way. I'm going to consider a set in C times K plus 1, K1 plus I, that on the left-hand side of the set equation, I multiply by the base. And on the right-hand side, I add the digits, but this is done differently as before. So here I am multiplying by the base, right? So this base is a complex number, but this base is also an element here because this extends the Gaussian rationals. So when I multiply a set here, basically I multiply component-wise. And on the right-hand side, I have this. So this may not be clear why I'm considering a pair, D. This will become more clear. But what I want you to notice is that D, again, is one of the digits from 0 to 5. From 0 to 4. So D is both a complex number and also one of these p-adic numbers. So I am translating F in this way. So using this, let's say, diagonal way. And so this is the definition of F, and I'm going to show why this definition makes sense. So suppose that we are considering a series in base alpha in this way. So alpha is the complex number the same as before, and J is one digit, right? The J's are digits in this set of digits D. So what I said before is that if I want to expand a complex number using a series like this, it will have multiple ways to do it. So one series of this form, it converges because alpha has modulus greater than 1. That is, everybody knows that. But also, this series is convergent in this p-adic space that I just defined, because exactly we define this space so that this happens. So alpha to the -1 has 1 plus I in the numerator. So when I get larger and larger powers of alpha to the -1, it converges. So what we can consider is that for such a series, I can consider two different limits. One limit is a complex number, and the other limit is a p-adic number. So I will look at a pair that I call x1, x2, and then on the first component, x1, I have a series that converges to x1, and in the second, I have the exact same series that converges to x2, but the two convergences are taken in different metrics. So this is this idea of the new dimension that I was adding. So for each of these series, I take, okay, the complex numbers that it converges, but I also give it a height. And the height is going to be this p-adic limit. So remember that I said that I had a problem because when I multiply a set by the base, the measure gets scaled by a rational number. So in the Lebesgue measure, the complex Lebesgue measure, alpha satisfies this. However, if I have a hard measure in this p-adic space, k1 plus I called it mu prime. If I have a hard measure, which is basically just the natural measure that would be defined in this space given its metric, when I multiply by this set, actually the measure gets scaled by 2. And that is because this 1 plus I that is in the denominator, let's say it goes, yeah, it becomes a 2 here. So what happens? If I take this product space, I can take a product measure. And in the product measure, these 2 in the denominator here and these other 2, they cancel out. So this space has a measure mu, it's a hard measure, such that when I multiply by alpha, the measure of the set gets multiplied by 5. So this set is actually self-affine because the set equation satisfies what I want to, that I have the same number of translations as how the measure gets scaled. And then one consequence of this is that if I take points in here, in this space, then I actually get unique expansion almost everywhere in this base. So let me go back here. So if I take x1 and x2 in this space, I can always find a series of this form such that that series converges to x1 in C and to x2 in the p-adic metric. And this is unique almost everywhere with respect to this hard measure. So this is the set that I get. So this is an illustration that, of course, is not completely faithful because this set is not in a Euclidean space. So the way that I represented it was by taking slices. So imagine that this vertical line is the third p-adic dimension, the floor is the complex plane, and then this set is a union of slices, each of which is actually a fractal set in the complex plane. So to be more formal about these slices, so for every point in this p-adic space, I take this space, which is basically a copy of C, and I intersect F with this copy of C. So what I get is a slice, which in general is empty, but for a countable number of points, it's non-empty. And then F, I write it as a union of such slices. So to justify a little bit my presence in this conference, this is related to dynamical systems. So there are ways to individually compute these slices using certain maps, which is actually very interesting. But again, I don't have that much time to define that. But yeah, each slice can be computed individually. That's how I made the pictures also. So F, the new F, this curly F in this three-dimensional space is a self-affine set. So it's the union of smaller copies of itself. So suppose that I take F, this three-dimensional set, and I write it as a union of smaller copies of itself. And suppose that I take a slice. So when I take a slice, each of these subdivisions, I will also get a slice. So basically, when I look at a slice of F, I can see that each slice is a union of other slices. So each slice can be subdivided into smaller copies of other slices. So there is one particular slice, which I call the zero slice, which is obtained if I intersect F with, let's say, the floor with C times 0. So this is, in my picture, is the slice that is at the bottom. So it looks like this. So you can already see that it's similar, for example, to the twin dragon. So it's a set that already has a fractal boundary, has positive measure, blah, blah. So in this illustration, I consider this zero slice. So imagine that there is a third dimension here that we are not seeing. And then imagine that this is the slice of this bigger set, but that bigger set is subdivided into smaller copies. So this is the zero slice of the big set. This is the zero slice of one of the smaller copies. If I subdivide that small copy again, I get this one. If I subdivide again, I get this one. So I have like this nested sequence of sets, all of which are the same set at different scales. And actually the intersection is 0. So originally I did not have a self-affine set. After I did all of this study using this p-adic completion, I got something that is self-affine, not in the exact same way, but a set that is contained within itself. And actually this is simply just a set in the plane. So I did all this construction of the new space, but then by taking the slices, I came back to the plane. So this was the set that I had originally. And now with this idea of adding a new dimension, this is what it looks like if I only stay with the points that belong to this zero slice. So yeah, I thought this was a nice picture to go from here to see how this new space actually makes things also more beautiful. And of course, I can continue subdividing the set. So for example, here is another iteration. It's rotated, but it's the same set as before. This is another iteration in which more slices of F appear. And these slices, now I can imagine them just being in the plane. And actually, this subdivision into slices, this gives me a tiling of the plane, where each of the tiles are different in principle. So you can see that they're all similar. Some are more similar to others. So then we can imagine that in the integer case, so like in the case of the twin dragon, I had one set that tiles the plane. Now in this rational case, I have a family of sets that tile the plane. because of course this can be iterated infinitely. Yes, this is a final picture of also a patch of this styling. Thank you very much.
Yeah, any questions?
Yes. Finally, many primes. Yes. So the way that this was done originally was by taking generally just an algebraic number and then looking at the field spanned by this number. In this example is Q of I, but in general, it can be another field, Q of alpha. In Q of alpha, you may not have this notion of Gaussian primes because it may not be that the ring is the ring of Gaussian primes. But what you have is what is known as a Dedekind domain. So a Dedekind domain is a space in which every ideal can be factored into prime ideals. So that's also why I wanted to explain a particular case to not get into the more difficult setting of prime ideals. But yes, you can take finitely many primes. One way that you could do is instead of adding one dimension, you just add a product of dimensions. There is another way to do it, which was actually kind of like one of the main lines of my PhD, is that instead of looking at these prime completions, you take a space that is defined as a projective limit. So instead of you forget about primes, you forget about the prime factorization, and then you define a space that does what you want it to do, which is that this series converges in a sort of p-adic way. So actually, even if you have finitely many primes, you're still just adding one dimension. Even if you have finitely many primes, because yeah, if you think about it, so for example, this could be thought of instead of taking, let's say, in the rational case, Q2 times Q3, you could take a space that is like Q6. So instead of 2-adic times 3-adic, you could actually define something that is like 6-adic. So you don't really need the primes. Yes.
Can you go to the slide where you said something about dynamics?
Yes.
Can you explain how to do that? Like, how did you obtain those individually by using dynamics?
Yes. So there is a map that one could use to, so I said that when you have a complex number, you have infinitely many expansions, right? In principle, in this base using these digits. But in this zero slice, actually, each point will have only one expansion. Because of all the possible expansions, I'm looking only at one expansion, which is the one such that on this third dimension that I added, it converges to 0. So one could define a map such that if I have this, so this map has to do, is related to this, kind of right here. So suppose that X is in, so this is for the integers, but it could be done for rationals. So if I have a number X, I can have a map like this, and then X gets mapped to this, and this D is the only digit that makes this again in C of alpha. So that's why it's important that I take a residue set at the beginning, because this is the unique digit that does that. And then using this map and using something called shift radix systems, one can define these sets by, I don't want to say something wrong. I don't know if I remember the definition exactly, but basically taking pre-images of this, so using this dynamics, you can actually just simply pick the points exactly that belong to this set without having to actually go through this p-adic. Yes.
Any other question? If not, let's thank Lucia again.
Thank you.
Hi everyone. Today I'm going to talk about realization of Choquet simplices as the set of invariant measures on minimal homeomorphisms of manifolds. It's a long title, but I'll explain every bit of it, at least try to explain. This is an ongoing project with Yerney, Till, Dominic, and Piotr Proha. So for some background, by a dynamical system, here I mean X, a compact metric space, and T is a continuous map. And MT of X will denote the set of all invariant probability measures on X. Since we are talking about Choquet simplex, the question is, what is a Choquet simplex? It's a compact convex subset of a locally convex metric space. Okay, it's a definition. But how is it important for us? So the important property for a Choquet simplex is that every point inside this Choquet simplex can be written as a unique generalized convex combination of its extreme points. Why I am talking about the generalized convex combination? Because the set of extreme points might not be finite. I might not be in the finite dimensional Choquet simplex. And why Choquet simplex or Choquet simplices are important? So it is a well-known theorem that for a topological dynamical system, the set of invariant probability measures forms a Choquet simplex. Now, the other way around question would be, like from this statement, I know that for every topological dynamical system, the set of invariant probability measure is a Choquet simplex. The other way around question is, what if I am given a Choquet simplex? Can I construct a topological dynamical system which will have the same or similar set of invariant measures? And this is the motivation to the question, that what class of dynamical systems can you describe so that every Choquet simplex can be realized in this subclass of the dynamical system? And this question was answered by Dovnarovich in 1991, in which he proved that for every Choquet simplex, you can construct or there exists a minimal subshift such that the simplex of its set of its invariant measures will be affinely homeomorphic with K. So this gives us the answer that the class of dynamical systems here is this set of this minimal subshift. And the further question which we can ask ourselves is that, can I, given a Choquet simplex, can I construct a minimal homeomorphism on a manifold? So to extend the minimal map on the subshift, can I construct a minimal homeomorphism on a manifold so that it can realize my Choquet simplex? And this is the question we are trying to answer in this project. And the theorem, so this is the main theorem of our project, which says that if I have a manifold with a dimension greater than equals to 2, and I have a minimal and uniquely ergodic homeomorphism. So this is minimal and uniquely ergodic homeomorphism already there on my compact manifold, and I am given some arbitrary Choquet simplex, then I am going to construct another minimal homeomorphism, or in case where my Choquet simplex is unique, then the minimal homeomorphism will be the same. But I'm going to construct a minimal homeomorphism which will realize my Choquet simplex, so which will have the set of its invariant measures as this Choquet simplex. And how are we going to prove this? So okay, by ergodicity, I mean that the measure is ergodic if every T invariant subset has a trivial measure or full measure. And any dynamical system or any system is minimal if the only proper non-empty closed subset, there exists no proper non-empty closed subset of this X. So to prove the theorem A, we are going to use another theorem, a black box theorem, proved by Beguy, Krovitsia, Laroux. Okay, there is a lot of text. I'll try to explain you with this diagram that what does this theorem says and how it will help us to prove our theorem A. So this black box theorem says that if I am given some minimal and uniquely ergodic homeomorphism on a compact manifold with the dimension greater than equals to 2. So the setup is same as what we have in our theorem A. And I am given some homeomorphism on some Cantor space, then I can construct a minimal homeomorphism F tilde, which is universally isomorphic to F times G. The property of universally isomorphism, which is important for us, is that the two maps are universally isomorphic, implies the set of their invariant measures has an affine homeomorphism between them. And this is what is most important for us. So now by black box theorem, we already have a homeomorphism F on the manifold. We need to construct some Cantor homeomorphism so that when we put these two things in this black box, so in this theorem, we can obtain this F tilde, and we want to make sure that the set of its invariant measures is affinely homeomorphic with K. So to be able to obtain this, we need to prove now the set of invariant measures of this set is affinely homeomorphic with K. So basically now my problem has reduced. Instead of finding a minimal homeomorphism on a manifold, my problem has been reduced to finding a simple Cantor homeomorphism with some properties. And therefore, that is my theorem B, which is we call reduced theorem. And so what does this theorem says? So if I'm given a Choquet simplex K and I have an irrational number alpha, then I can construct a Cantor homeomorphism G such that this system CG is the topological extension of the irrational rotation R alpha. By a topological extension, I mean there exists a continuous and onto map which commutes with the maps in the spaces. Also, yes. Also, I need the simplex of its invariant measures is affinely homeomorphic with K to be able to obtain what I need in the theorem A. And also, I need the isomorphism between, so for every ergodic measure on this Cantor homeomorphism, I need that this measure preserving system is isomorphic with my irrational rotation. And this isomorphism will make sure that the system which I'm constructing will have the spectrum exactly as the spectrum of the irrational rotation. So, and once suppose I have been able to prove theorem B, then how does it helps me to be able to apply in my black box theorem and obtain the theorem A? So I choose an irrational alpha from this. I have a manifold. I have a uniquely ergodic and minimal map on the manifold. So from this, the spectrum is countable. So we can choose some irrational alpha, which does not belongs to the spectrum to preserve the disjointness. And then on this irrational alpha, I use theorem B to construct the Cantor extension of this irrational rotation. And I also make sure that for every ergodic measure, because of the spectral disjointness, the system's Cantor system and my manifold system are disjoint. So once they are disjoint, I have this first homeomorphism because of the black box theorem. And then I can obtain the second because of the properties of my Cantor system. And I know that this set is, because my F was minimal and uniquely ergodic, this set is just one measure. And from my theorem B, I already have that simplex of its invariant measures is K. So this set will be affinely homeomorphic with K. And thus I have obtained the theorem A, that simplex of invariant measures of minimal homeomorphism is affinely homeomorphic with K. So from this black box theorem and reduced theorem, from this black box theorem, I get that to prove theorem A, I only need to construct a Cantor homeomorphism with those properties, which is not an easy task, but better than constructing a homeomorphism on the manifold. So how do we start? So this, I'm not going to explain you the entire construction, but I'm going to give you an ingredients, an idea of the construction, that how does it follow. So what are the ingredients which I will need to construct this Cantor homeomorphism? I would need an irrational rotation on the unit circle, because we are constructing a topological extension of the unit irrational rotation. And then I define a special function called marked semicocycle, which is a function from unit circle to the symbols 0, 1, 2, and they have the special properties. So I have fixed a gamma, some arbitrary number, and I have called this gamma to 1 to be a marker interval. And I fix that my function will always have symbol 2 on this marker interval. And on all other places, it can have either symbol 1 or 1, but not 2. And this marker interval will make sure when I go with further in the construction that my irrational rotation is always visible in the dynamical system constructed using this Mark semi-cycle, and has at most countably many discontinuities. So what I can do is take this interval 0 to gamma, and I partition this unit circle with left closed, right open intervals, such that every point on the boundary will be the point of discontinuity, and every point inside this interior point of these intervals will be the points of continuities for f. And then using this f, I can construct a minimal and uniquely ergodic subshift over the symbols 0, 1, 2. Now, why are this minimal and uniquely ergodic subshifts important? So these are my base subshifts, and the Cantor homeomorphism or the Cantor system which I want to construct will be constructed using those base subshifts. So I will construct base subshifts, and then I will go through an inductive construction to obtain the final subshift I need. Also, I would need another black box theorem where I will reduce the problem of arbitrary Choquet simplex to the problem of Bauer simplices. Now, what is a so first, what does this theorem say? And then I'll explain what is Bauer simplex. So what does this theorem say? It says that if I'm given an Choquet simplex, then I can find a decreasing sequence of Bauer simplex such that this Choquet simplex can be written as an intersection of those Bauer simplices. Bauer simplices, so for Choquet simplex, this statement is not true. Like the extreme points of any arbitrary Choquet simplex is not closed. It could be dense, for example, for full shift. But Bauer simplices has the property that its set of its extreme points. So the set of ergodic measures, let's look at it in this way, is closed. And this is a very useful property. I will show you how it will help me in the construction. But this is a very useful property. So by Edwards theorem, I can write my arbitrary Choquet simplex as the intersection of the Bauer simplices. And these Bauer simplices are Kn's. And the extreme points of Kn's is a closed subset. So because it's in a compact, so it's a compact subset. And this is the important property of the Bauer simplex, that in an arbitrary Choquet simplex, I take an arbitrary Choquet simplex, I take the set of its extreme points, and then I make a convex hull of it, then I will not obtain the initial Choquet simplex again. This is not true in general for Choquet simplex, but for Bauer simplices, they are true. Like if I take the extreme points of Kn and then construct the convex hull of these extreme points, then what I obtain is a finely homeomorphic with my original Bauer simplex. And I also need, so these are all the ingredients which I need. So I need a Edwards theorem, and I also need an homeomorphic embedding from compact metric space to the space of all Mark semi-cocycles. So the Mark semi-cocycle, which I defined in the previous slide, I've just introduced some metric in it, and I construct the space of all Mark semi-cocycles. And because, as I said, for every Mark semi-cocycle, I was able to construct a unique ergodic invariant measure. So therefore, indirectly, I am trying to construct a homeomorphic embedding from an arbitrary compact metric space to the space of all in ergodic invariant measures on 0, 1, 2. Now, so what is the idea of the construction? The idea of the main idea is to construct some special sequence Pn with the properties that Pn from this Bauer simplex sequence Kn to the space of all invariant measure is a continuous embedding, and for any epsilon, for any sequence epsilon n which going to 0 fast enough, I make sure that the point Pn of z is epsilon close to Pn plus 1 of z in the metric, respective metric, which is like weak star metric, because they are, Pn is a mapping from Bauer simplex to the space of invariant measures. So this Pn of z, Pn plus 1 of z, they all belong to this space of invariant measures on 0, 1, 2. And space of invariant measure has a weak star metric. So we can talk the epsilon closeness of those points. And then once I have this type of sequence, then I define for every z in key the limit of this Pn of z my each Pn of Z is a continuous embedding, and by making sure that at every stage they are epsilon n close, I can have a P infinity map, which is a continuous embedding from my arbitrary Choquet simplex to the space of invariant measures. Once I have obtained this, then I have my Cantor then I only need a subshift, which is realizing this Choquet simplex in M sigma of 0, 1, 2. Now, how do we construct this Pn? So first I do it in an inductive way to make sure that at every stage I'm also epsilon n close to the previous stage. So at n equals to 1, I start with the extreme points of K1. Here is where we use the compactness property of the extreme points of K1. Because I know K1 is a Bauer simplex, I know extreme points of K1 is a compact metric space, and I have an continuous embedding of extreme points of K1 to the space of ergodic invariant measures. So I define this green border is extreme points of K1. From this, I define this P1 tilde to some set of ergodic measures in my space of invariant measures on 0, 1, 2. And then I take the convex hull of all these red points. So once I have defined the mapping, I take the convex hull of all these red points. But because K1 was in Bauer simplex, the convex hull will be affinely homeomorphic with my K1. And then I can extend it to obtain a homeomorphism from the full K1, not just the extreme points of K1, but from the full K1 to the convex hull of the this set, so which I call K1 prime. So then I obtained an homeomorphism from K1 to K1 prime, but K1 prime is contained in the space of invariant measures. And in this similar way, and also making sure at each step they are epsilon n close, I construct the sequence Pn. And then the limit of this inductive construction P infinity will be an affine embedding, which we already saw. And that at every n step, not just making sure that my Choquet simplices are converging in a certain way, I'm also making sure that I am constructing a shift space at every step n, which has an simplex of invariant measures affinely homeomorphic with Kn prime. So here my Kn prime is a Choquet simplex in the space of invariant measure of 0, 1, 2. So I can have a shift here which will realize this Choquet simplex. And this shift I'll call by xn. And then we define x infinity as the Kartovsky upper limit of this xn's to make sure that the space of invariant measures of x infinity will be affinely homeomorphic with K. And at every step, I will also make sure that my each xn is constructed using those semi-cocycle, like marked semi-cocycle extensions. So those marked semi-cocycle were having irrational rotation as the topological factor. Therefore, my xn's will also have irrational rotation as a topological factor. And therefore, I'll like, by doing the word combinatorics, I will make sure that my x infinity will also have irrational rotation as the topological factor. And also, at every step, I will make sure that the system is isomorphic to the irrational rotation to make sure that my limiting system is also isomorphic to the irrational rotation, which will make sure that the spectrum of x infinity is alpha to the power n, and which will make sure the disjointness of this x infinity with my manifold to be able to obtain theorem A. And this will construct the Cantor homeomorphism. Thank you for your attention. It's an homeomorphic map, but it also preserves the convex combinations to convex combinations. So if I have A1 x1 plus A2 x2, then A1 P of x1 plus A2 P of x2. So. Sorry, again. So by semi-cocycle, I just mean like I'm not using the full extended properties of the semi-cocycle. Here it's a very special function with only countably many discontinuities. Full cocycle can have discontinuities of full measure. Right now I have the discontinuities of zero measure. No, not this semi. Like here it's like I'm defining it as semi-cocycle, but it's just a function from irrational to this, making sure it has a countably many discontinuities and Lebesgue measure 0. Yes. Okay, so space of space of invariant measures for the full shift. So the ergodic measures here are dense. So they are not extreme points.
I give the stage to Tita, who is talking about equidistribution on Tori.
Thank you very much for the invitation and everything. So I'm going to start my talk with some setting, and hopefully it will not be too hard for everyone. And also, please tell me if I'm writing too small. And then I'll present the main result between that has been like joint work with Gialunli and myself, a prime counting result and equidistribution formula. And then I'll so explain some corollaries. And hopefully I will have, yeah. Okay, now let me start with the setting. So it will be a bit abstract. You take G, the square D by D matrices with coefficient in R and determinant 1. Okay, no, it's not abstract. And A is the diagonal matrices with positive coefficients. And I asked them to be determinant 1. I have another notation for the logarithm of big A, which is this square Gothic notation. The matrices of zero trace. And also, this is called the positive Weilchamber, and I'm going to be asking the coefficient, the diagonal coefficient, to be in the decreasing order. So K is SODR. And I'll say probably a quick words for specialists later. And M is the centralizer of A in K. And here is the plus and minus 1 diagonal matrices. Of course, you want determinant 1. So what's the main problem? I'm taking gamma. So it's going to be co-compact, torsion-free, irreducible. And what I'm interested in, sorry, what I'm interested in is the right action on this like quotient space built out of a Lie group. And I'm interested in the compact orbits. So the main question is, how many? And what are the statistical properties of these orbits? So it's still abstract. It's heavy. It's a bit abstract. So I'm going to explain a bit what happens in the d equals 2 case. And then on the right is going to be the d bigger than 3 case. So in this case, G mod H is in fact, I mean, you can identify it with the Poincaré half space, which is like the domain of hyperbolic geometry. So it's a bit small, but this is constant negative curvature and it's the Beltrami surface. And the hyperbolic space means that at every point, you're like in some piece of this Beltrami surface. And of course, I didn't come with a dress, but I could dress up this Beltrami surface. And every participant is free to touch this very nice dress later on. So it's the realm of hyperbolic geometry, so constant negative curvature. And so G mod M is, in fact, the unit, the unit tangent bundle of the hyperbolic plane. And if I look at this action here, it's the same as looking at the geodesic flow. So if I play on my dress, I can have really like geodesics like this. I just need to pull it and it becomes straight line. So I understand how straight line goes. And also, if I quotient on the right by gamma, so I can, I'm in some genus G surface. And the geodesic flow goes like this. You take an arrow here, and then you flow around it. And then you look at what happens at some later time. So what are we doing? So I wanted to tell you about this result by Huber in 59, which is that the number of prime closed geodesics, prime closed geodesics, and I also want them to be oriented of length less than some time. I'll pull this up so that everybody can see. So this number is equivalent to exponential big T over T. So why is this called a prime geodesic theorem? It's because this asymptotic is like the asymptotics of like prime numbers, big N over its logarithm. Okay. So what happens in our case? I have to lift this one here. So CA is the compact A orbits. Okay. Of this homogeneous space. And if I take a compact A orbit, I can define a set of periods. So this set of periods lives in the Lie algebra because I want to flow on the right. So the idea here, if I take this small loop here, say this is my vector z. And if I flow like the length of the geodesic, I come back to myself. So the set of periods, in this case, it contains, of course, 0, and it contains the length here, and minus the length, and so on. Here, when d is bigger than 3, this is like, so this is like Euclidean lattice of A. So A is like R to the d minus 1. And okay, I'll give the prime counting that we have with Jalun and myself is that. Okay. So I have, okay. I take the intersection of the number of periods what? Sorry. Sorry. Okay. Okay, I'm drawing some okay, some false picture of what's happening, but this I hope the specialist won't bother me. Okay, if I do it like that, it makes more sense. And then I'm going to, so I have this like pizza slice here, and I have these period points, and I'm counting like the multiplicity of these points inside this ball. So inside this pizza slice, and I intersect. So this is the green set here, and this is like the set of periods. And I have like, it's like the length of the flat torus. And we have this, so some constant, an exponential term, and a polynomial term, plus and we also have the first asymptotic term here. So, so this is what we have with Jalun. So the idea is that because of this, like this is a big exponential term, we know that how the answer to how many is like a lot. And now the next question is, how do they equidistribute? So I'm not going to wash with, okay. And we have Bowen and Margulis theorem. So it was on the late 70s. So it's independent results. So I'm just going to write down one of the formulas they get. So F is just a prime closed geodesic. And I just take the lower integer part of the time over like the length of the geodesic. And this is like the arc length measure. On the geodesic. And they prove that, okay, I should just write down the normalizing terms as t goes to infinity. And in the dual of the C infinity functions here. And this goes towards, so the Haar measure. So it has several names. So people call it, people like me, okay, many people call it the Haar measure. Other people call it the Liouville measure. And still other people call it the measure of maximal entropy. Okay, what we have, so it's like, we have a Bowen-Margulis formula. So we are going to keep the same multiplicity term. And here, we are going to take, okay. So I'm going to ask to take a Lipschitz test function for any Lipschitz test function. And I'm going just to evaluate it. So this is like the Lebesgue measure on the torus. On A. So it's the quotient of the Lebesgue measure. Okay, it's the quotient of the Lebesgue measure on the torus. And of course, I need to divide by the appropriate terms. And this we prove that it goes towards some constant that depends on G. So still it's the Haar measure. So it's still the quotient of the Haar measure, and we have an exponential terms, which depends on the Lipschitz norm of F. So this is the asymptotics we have. And I did say that I was stating everything for SLDR and SL and any co-compact lattice, torsion-free co-compact lattice. You can take your favorite semi-simple Lie group, and it's way more general. It's just that I didn't want to add more pointy Lie group stuff to my talk. How long do I have left? 20 minutes. Okay. Okay. So I'm halfway through. Good. Yeah. Good. Any questions? Okay. So I wanted to point out a few things is that the rank 1 case and the high rank case, so this case here, the idea is that in this case, the systole and the volume are like the same number. Here, the lattices, they have like a smallest period, but they also have like a volume, and it's no longer the same. So it makes it slightly more complicated. I'll just erase here. And I'll present you a bit of an overview of what has been done in so high rank. So in the high rank case, we have a family of results. So the results as the systole goes to infinity. So the idea here, so I erased the picture, but it was a bad idea. Is that, so say this is my set of periods. If my time is too small, so I don't count this point here, so I don't count the torus. And if I'm here, I mean, I'm just counting the systole. So this term, like the volume term, will appear in my sum. So essentially here, I'm counting as the systole goes to infinity. So our result is here. And of course, you can also count as the volume goes to infinity. Volume of F goes to infinity. And I should say that the story started with Spazier in his thesis in '83. And he was counting as the systole goes to infinity. And he only got a counting result. And he only got this log growth because he said that this sum here is essentially the same as some, he was using some dynamics arguments. So he only got to the logarithm of counting term. And so he got to this mysterious entropy delta 0. There is a time gap, and then we have the results of Teichmüller. I forgot the timeline, but I think it was 2007. And so I said, Jialun and myself are counting in balls. Teichmüller was counting on parallelotopes. So this is and he was relying on some methods that are like almost the same as what Huber was doing. So Huber was relying on like some very celebrated methods called the Zellberg trace formula. So he was relying on this trace formula, but in high rank. So it was like a different domain. And very lately, we have some result of Guillermo. Bontono and Weich. And Weich. So I think it's still it's very recent. And so their methods can be understood as micro-local analysis. And real resonances in high rank. Okay, so there are different methods to attack the problem as the systole goes to infinity. As the volume, as the volume goes to infinity, so we have like the celebrated works. So for the finite volume case, so non-co-compact case. So for SL 3R mod SL 3D. So for this case, you have the celebrated works of Zidler, Lindenschloss, Michel, and Venkatesh. And the specialists write this paper as ELMV. Sorry, but this was in, I think, 2011. And they took families of periodic torides, and they proved that these periodic torides of the same shape equidistribute towards the Haar measure as the volume goes to infinity. They don't actually get a counting asymptotic. So, and it's very much celebrated works. Okay. So maybe I can write down some corollaries of these formulas. So the first idea is that if you have the equidistribution formula, you just use it for the one function here, and you get to this function above. I mean, you get to the result above. So it's I mean, it's quite nice. But what you can do, which is even better, I don't know if it's even better, but you can look at sorry, okay. So far, we were only doing dynamics and looking at the tori here, but you can instead look at the conjugacy class of elements in the group. So a bit like in rank 1, a periodic geodesic is the same as the conjugacy class of a hyperbolic element in the group. So so you have like a consequence for wait, how long do I have? Oh, okay, I think I can make it. 20 minutes. Okay. So this is going to be annoying. Okay, I'm just So those who know it know that this element is called the broaden projection. In rank 1, it's the length of like the translation length of your hyperbolic element. And there is also a linear algebra description. So provided gamma is co-compact, so there exists an element in the group G, some compact element, and so you have this element which is like in the closure of the Weil chamber. Let me erase this. So such that, so these elements are going to commute. And this is just a diagonalization of your element here. So, and this defines your Jordan projection. And okay. So we're going to be interested in a very small subclass of elements in gamma. It's called the loxodromic elements. It's the elements in gamma such that their Jordan projection is in the positive Weil chamber. And so I'm going to state a very surprising lemma by Zellberg. Okay, it surprised me when my co-author pointed it out to me, and some other people also pointed it out to me. But if you take any loxodromic element and you diagonalize it, then you can look at this flat torus here, this specific A orbit here, and you can denote it like F gamma is a compact orbit. I should say that it works because gamma is so it's gamma is co-compact. So under the co-compact assumption, of course. So with Jalloum, we then noticed that if you have a loxodromic element, so the conjugacy class of a loxodromic element, it's going to be in a one-to-one correspondence with, so this will give you a regular period of this flat torus. This is Zellberg. And so this is in one-to-one correspondence with the tuples with when the left part is a compact A orbit and the right part is so an element in the positive Weil chamber, but also a period of F. So this map is well defined. And the idea is that you have a one-to-one correspondence here. And this allows us to, with some more work, to deduce that if you look at the number of conjugacy class of elements in gamma with their Jordan projection of norm less than T, it is dominated above by, so it's exponential e over t to the r plus 1 over 2 as t goes to infinity. And I think I will have time to show one picture and then I will go over. Yeah. 10 minutes? 15? So much? Okay, then lastly, I guess I will explain so a quick computation. The idea is that if you take this asymptotic here and you divide it by TR, which is like the expected which is like the expected volume that you want for any torus, like any balanced torus, like the one I drew here. You're getting like it's really too elementary. E over R plus 1 over 2. To get the lower asymptotic, you need to know like the statistical properties of the shapes of your torus. Like you need to know that most torus will have good shape, and then you will get the lower asymptotics. So here we only get the upper asymptotics. And I can explain to you also. The volume counting asymptotics. So this is like ongoing, but so it's ongoing, and I think we added another coauthor. Gargava. Ah, right, good question. R is d minus 1, and it's the dimension of A, the R dimension of A. Yeah, thank you for the question. Yeah, I'm sorry I didn't, yeah, I noticed that all these formula had R all over the place. So now if I try to get back to counting the tori, but with respect to the volume. So the number of toris. So I have a partial result. I don't want them to have regular singular periods. So what I do here are like the walls of the Weil chamber. Okay, and with the volume of my tori less than some constant v, this so the idea here is that by Dirichlet theorem, the idea is that you have some so this is for those who know, this is the Weil group. The Weil group, and then you have this relation, but for square root of r, v to the power 1 over r. Okay. Yeah. So the picture is simple. If I pick a torus of volume less than v, I know that my shortest vector has to be length less than square root of r, v to the power 1 over r. So I have like a direct relation with this like conjugacy counting. And so I can deduce like the volume counting upper asymptotics in logarithm. And similarly, it's the same problem if you want to if you want to have the lower asymptotics, you need to understand like on average how many tori are like balanced. So it's like the same problem. So that's what we were doing recently. We were trying to get back to volumes because we were playing with the systole and we're trying to get back to the volume. And now I guess I can finish by showing you two pictures. Okay, so this picture here. So here you're interested now not in compact orbits, but on divergent orbits. So it's an illustration of a theorem by David and Shapira. And all these lines are like geodesics. They are geodesics that point to the cusp. So really like this part here. They come from the cusp, they bounce, and then they go back. And David Shapira proved that these divergent orbits, they equidistribute in the like moduli space. So the idea is that if I point out my finger here, I see that almost like close by, I'll get any directions of unit tangent vectors. So that's an equidistribution picture. And next. So we wanted to understand like the shapes of these flat tori's that we have. And here, so we were studying a family of like a family of flat tori that we could numerically generate. And what we found is this is like the cusp. So it's the same as infinity on the other picture, but except now it's reversed. And here we see an escape of mass in the cusp. So there are way more points here. And up there, it's sparse, and I didn't have that many points. And I think we're trying to cherry pick elements in this family to prove density of shapes. But right now, if I'm brute forcing like with my computer and drawing everything, then I guess I get with these families of flat tori, I mostly get unbalanced tori at some point. And then it creates a lot of numerical errors because then like the computer decides that no, this number is too close to 0, I don't like it. And then it crashes my computer. But this is I mean, this is already quite good, so you can represent the shapes here. And thank you for your attention.
So thank you first for your talk. Are there any questions? Then I might ask you something. So you had you were mentioning these different methods to count, so either to take like a circle or to take a polygon. I mean, I really have not that much of an idea. So for me, it sounded very similar because like you can put basically the one into the other when you just increase the radius. So can you say maybe 2 more words? What is the main difference of it?
Yeah. The idea is that if you change the shape, your volume, I mean, it's related to growth of different shapes of balls in the Lie group. So maybe a quick word. and it's so it's if I look at the volume, so in the Lie group of something, so this is a ball here. So if I take so yeah, I'll write down Dithmar domain. So it's a parallelotope domain like this. Here. So the asymptotics as t goes to infinity is purely exponential. So it's another coefficient, but it's purely, okay, I probably want a constant here, but this is like purely exponential. Because R shape with Jaloun is like rounded. Because it's rounded, we had that polynomial, and also the coefficient is different. So the coefficient depends on the volume growth, and maybe I should, like, we could recover some counting result like that of Dithmar, in the sense that if you change it and here you put a parallelotope, forgive my orthograph. Here, so this crashes, so you also get, and then you have another shape, and it's 1 plus O exponential minus ut. So if you change the shape here, you get another asymptotic. It was just a bit, yeah, I don't know. So I don't know if it answers your question, but
Any other questions? Okay, then let's thank Tidang again. Okay, welcome back to the next talk by Caroline Wormell, who is talking about Chebyshev methods for Anosov maps.
Thanks, Tanya. Well, thanks for having me here and inviting me to give a talk. Oh, no, rather accepting contributor talk. So this talk is really kind of computational. It's about, well, okay, I suppose chaotic, some very accurate numerical methods to study long-term ergodic properties of a class of chaotic maps. So, okay, I suppose we like to study, as dynamicists, we like to study particularly nonlinear maps. The thing about nonlinear systems or nonlinear things in general is they're hard. So a very natural thing to do, thing that is very common, is to study linear operators. And so these are, of course, you know, if you really want to preserve what the nonlinear map is doing, you need to go to kind of some sort of infinite dimensional thing. And in particular, we go to infinite dimensional operators on functions. So we say functions on the phase space, and we try and do things to these functions on the phase space. And one thing we can do is apply what's called the Koopman operator, which is just basically function composition by the map, which is easy to write down, but perhaps harder to understand intuitively. And we can also, but we can sort of apply its kind of dual, which is the transfer operator, which more or less what it does is it takes a measure density. This is phi here is now measure density, and it pushes it forward under the dynamics. And this is the measure density you get out. So you get some Jacobian term that's mostly not particularly important, at least in this talk. And you also get a sort of composition here by the inverse of the map. And so perhaps again, they're dual notions. If you integrate with respect to Lebesgue, you can sort of swap them over. And there's a lot of important information in their spectrum and resolvent and so forth, which we have seen a little bit of, and we will see a lot more of probably. This is the handout version. That is not good. Okay, it's fine. Okay, so, oh no, it's fine. Yeah, so we can also sort of adjust transfer operators a bit to get more info out of them by putting some different weights in here. So instead of JF dash, you get W dash, and that sort of adjusts your Koopman operator as well. But it's not particularly important. For this purpose of this talk, so mostly there's no analytic solutions. You know, if you want to look at the spectrum, for example, of these operators. So we have to do some, if we want to know, like get a specific answer, we have to actually look at the, we have to compute with things. So if you look at perhaps the simplest class of chaotic maps, which are, well, let's say uniformly expanding maps, which are full branch, I'll show you to next slide what that's about, or in the future. There are a bunch of ways we know how to do this. One of them is dynamical zeta functions, which is basically you compute a lot of periodic orbits. And with these periodic orbits, you can estimate some sort of Fredholm determinant, and this will tell you a lot of things. There's Ulam's method, which is kind of really the simplest thing you can do, which is basically you take particularly, well, one of these two operators and you discretize it using you just sort of look at what it does to piecewise constant functions, and you get something that works for a lot of systems, but is quite slowly converging if n is the number of sort of pieces that you allow. But perhaps the best thing that you can do with these systems is apply, say, Chebyshev or Fourier methods, which discretize these operators using Fourier series or Chebyshev polynomials, which are kind of similar. And so they, I mean, they're really, if you want to get a really accurate estimate of something, which is quite useful if you're trying to do sort of something a bit strange or a little bit close to a singularity, you can get, say, exponentially good estimates here if your map is smooth enough. But of course, we might say, well, this is just these are very simple models of what chaotic systems do, and maybe we want to become a little bit less simple. And one direction which we can do this is by studying systems with expanding and contracting directions. So I guess these are called Anosov systems. Well, the simplest way to do this is Anosov systems where the expanding and contracting directions are kind of isolated from each other. We know we have some cones actually which tell us approximately in what direction the contraction in phase space and the expansion in phase space is going on. They're not very realistic if you care about realism. I think this is about the only system, these kinds of mechanical linkages that Robert Mackey built a bunch of, are kind of the only examples of things that in real life that we see that are Anosov. But, a sort of lot of algebraic examples or geometric examples, including particularly geodesic flows, are Anosov systems. So, in some sense, it's motivated to try and study these things. I think we know that dynamical zeta functions you can do stuff with. We don't really understand why it works with Ulam, but they're not, it's slow. But so it would be nice to see if we can use these Chebyshev methods in the case of 4 Anosov systems. And of course, this is a little bit hard because the contracting directions change a lot of things that we'll see in terms of kind of the functional analysis of it. And there's been some preliminary work by various people have had a go at it on Fourier series. I think the sort of paper that's out is by Harry Crimmins and Gary Froyland about 5 years ago, and they were sort of trying to make it positive. But anyway, it's really fundamentally, if you have a Fourier series, you need something on a compact surface that needs to be a torus. Most surfaces we know are not tori. So I will try and talk to you about something that will work for things that are not tori. And the way that it works basically is by dividing your funky surface up into rectangles. But perhaps to explain the structure, we'll talk a bit about one-dimensional maps, then go to Anosov maps. So those are kind of these Anosov maps with contracting directions, but on rectangles, and then talk a very little bit about how you can go to more general kinds of geometry. So I suppose 1D, the kind of maps we want to think about have graphs that look like this. So basically you divide obviously everywhere the derivative is positive and it's continuous except when it hits the boundaries. But what happens kind of in between hitting the boundaries is that you have a bijection from, these subdivision of your space onto the whole image. I mean, they look kind of artificial, and they are, but for example, the Gauss map that gives you continued fractions is this. There's all sorts of examples as to why you should care about these things. But if you I suppose the key thing to understand here is that if you have if you look at the inverse of f, well, obviously it's multi-valued, but if you sort of look at the single branches separately, you have a countable collection of actually contractions, because the opposite of that. Okay, so that's great, but we're going to study Chebyshev polynomials, which have their own sort of funny little theory that involve basically being transformed from Fourier series by a cos transformation. So actually, we actually want something a little bit different. We want that this conjugation of our map is uniformly expanding, but in practice, that's not really a problem for various reasons. But I thought I'd just say it. So the idea of a Chebyshev series is, well, I mean, it was something when I first discovered it, it was quite surprising. I was like, I thought you couldn't do approximation on polynomials, on good approximation on intervals that weren't periodic. But turns out that if you take a sort of Fourier cosine series like cos k theta, and you just sort of take a transformation from a periodic interval to a, say from 0 to 2 pi to -1, 1, you can do all the same sorts of things, and you get these things. These are actually polynomials. You get these things out here, and you can see they're all kind of wavy and oscillatory, but the waviness increases as you get closer to the corners of the edges of the interval that you're approximating on. So they're orthogonal on -1 to 1, the range of cos, with respect to this weight here, which is just the Jacobian of this cos inverse of x transformation from Fourier series. And you can therefore, like with Fourier series, you can approximate them. You can approximate functions by, or rather you can write functions as series that look like this. And again, you have a kind of orthogonality relation, but you have to worry about this weight here. And of course, the nice thing about the series is that if you want to approximate this function by some polynomials, you can truncate very easily. And as with Fourier series, the sort of regularity of these guys of a function is related to the decay of the coefficients here. And so if we want to think about some really regular functions, we could study phi of, we can sort of think about functions here that have coefficients that decay exponentially quickly. So if we say here's a Sobolev space of functions with, where this sum here is finite, and the norm is basically this sum here. Every function here has Chebyshev coefficients that decay as like e to the minus rho k. And well, it turns out you can actually show that these are analytic functions, and they extend to what we call a Bernstein ellipse, which are, well, for various parameters rho, so various rates of decay, they sort of basically extend around -1, 1 in complex space. And you can show that if this norm here is equivalent to, it should be equivalent, that's not exactly equal, but these two norms here are equivalent if you take an integral, an L2 integral around the edge of your Bernstein ellipse. That looks the same. So it's a sort of measure of how analytic you are, or how much you blow up in analytic space. So what does this got to do with dynamics? So the transfer operator has some connection to this. If we try and study, if we think about what the transfer operator does, it takes, well, let's say like nasty functions, and by nasty, I'm going to say they're quickly oscillating. They're just like, they're one of these Chebyshev polynomials, say, but high order. You apply your transfer operator to it, and well, what you have is somehow like a sum of a bunch of different things. And all these things involve composing your oscillatory function with contraction. So you're stretching it out a bit, like hit like this. You can see that this is sort of the edge of that. And this is the edge of that. And then you're multiplying it by this Jacobian. So the Jacobian is, I mean, I suppose basically it's the derivative times of your contraction times some, constant to make it non-negative if it is negative. And you see that, so you're multiplying by some smoothly varying function, and it turns out that by stretching it out, you get something that is sort of less oscillatory. Obviously, it looks more ragged, but if you think about what kinds of frequencies you're seeing here, they're all lower than this frequency. So, and in particular, if we kind of decompose the frequencies in this, I take a Chebyshev series, we would see that, for example, we wouldn't see very much of this. The sort of amount, the coefficient in front of this polynomial in this would be very low. So we get some sort of result like this, and we can prove that. We can actually extend it a little bit more for when j is bigger than the sort of rate of contraction times k. So I suppose this is a theorem, in fact, that for one of these sort of C expanding maps, which is like an expanding map that's analytic, we can find two Bernstein ellipses so that actually we can extend these contractions, which are the inverse of the expanding map, to a disk. So you know, like they'll extend out to some Bernstein ellipses, and it will contract a big Bernstein ellipse into a little Bernstein ellipse, and from that you can get this kind of quite clean bound here. And so if you want to sort of take kind of heat map of where these coefficients, so you think about these LJKs as like the matrix like if you took a Chebyshev transform of your transfer operator, this is like, you get a matrix out, like taking a Fourier transform of an operator, you get a matrix out, and this is sort of, yellow says that these entries here are big, these entries here are ridiculously small. They're exponentially decaying. Now, I mean, you know, if you wanted to prove some sort of like compactness, for example, you'd look at this and you'd be like, well, all these entries here are, you know, really large, or they're non-zero. Like, it's not particularly, I don't know that it's compact or bounded or anything like this, but we're not looking in our Banach space here. We actually sort of want to tilt it a little bit. So tilt it by these weights in our Sobolev space. And well, okay, if we try and take a sort of Frobenius norm type bound of norm of any operator in this H row, this Sobolev space we've come up with weighting our Chebyshev coefficients, we get this sum here. And if we look at what this looks like for L, it has this appearance here, and you can see that these entries here are quite big in the corner, but then they decay exponentially quickly with that log scale everywhere. And so we could, just using the Frobenius norm, we can prove that our transfer operator L is compact and bounded and compact in one of these Sobolev spaces. Well, actually, we can also prove, we can also prove actually that if we say, okay, well, on my computer, I'm just going to try and compute this like, you know, the coefficients here in this matrix here, 60 by 60 set of transfer operator coefficients. Then the sort of operator norm error of that, you know, finite approximation of my full transfer operator is, oh, that should be order k times e to the minus r k. So it's exponentially small. And then there are two exclamation marks because exclamation and exponential, I don't know. So this suggests that Chebyshev series are really good, and it turns out they actually are. It's quite easy to do this numerically. I'd like to actually, you know, write an algorithm down to do this. We basically use some idea of fast Fourier transform, and you get estimates that go down very fast, where the error goes down very fast. Okay, so that's kind of the 1D picture. But now we want to think, well, what happens if our map is contracting? Well, okay, we want to think if it has both contracting and expanding directions, but let's start with contracting just by itself. So what happens there really is that you, well, so if we go back to this picture, I'm sorry. If you go to this picture, the fact that this VI, the sort of inverse of F, was a contraction meant that it sort of pulled this guy out. If F is contracting, then the V is kind of, you know, expanding, I guess. So it's pushing, if you try and think about it, it's pushing composition with this V is going to push it all together. It's going to make it nastier, progressively nastier. So this H, these Banach space isn't going to work, which is always the problem with chaotic systems, because you have to keep changing your Banach space when you change the dynamics. But the Koopman operator actually is, well, okay, if F is a contraction, then we're composing with a contraction. And what we've seen is that makes things nicer. And so this guy here is now bounded in H row. And so if we think about this kind of duality, we could perhaps create a dual space where L is bounded. And the norm now that you see is the norm of this sort of thing that we're applying our transfer operator to, of this contraction, is something where we're weighting high order coefficients down, heavily down, negative. So the high order coefficients could blow up really, really fast. But as long as they're blowing up slower than this, is getting smaller, this thing will live in this Banach space. So they're kind of spaces of like distributions. They're not really functions. You know, you could think of them as containing things like Dirac deltas or derivatives of Dirac deltas, or, you know, analytic continuations of Dirac deltas. So they're kind of, you can get a nice transfer operator and you can actually do all sorts of calculations with it, but you're working with functions that are really gross, things that are not even functions. So I guess to think about, if we try and take that understanding to Anosov maps, we now have, well, okay, let's start with rectangles that look kind of Anosov. So now what we're going to do is we're going to define maps which have directions where you have a lot of squeezing, and say that's vertical, and a lot of expanding, stretching, which is horizontal. And so what these maps are going to do, just sort of, I guess intuitively, is they take this piece here and they go squish and they go pull, and you get something out that looks like this. And maybe you have a bunch of different pieces, and maybe they don't all, whatever. Like the main point is that the ends line up with the ends here, as you see here. Maybe you can have some holes. It's not particularly important to the kind of, maybe dynamically it's important, but to sort of transfer operators, it's not important. And I guess there's kind of a meta theorem which says that you get nice Banach spaces for these Anosov systems if you look at what we call anisotropic distributions. These are distributions that are, this is sort of a picture of something kind of an anisotropic distribution. This is an attractor actually, but attractor's attractor of a chaotic system, but these kind of tell you sort of what you should be thinking about. They're smooth in expanding directions. So this is a perturbation of a cat map. So the expansion is happening in this direction, and then they're kind of really ugly and fractal in this direction. They're like Dirac deltas or that sort of thing, derivatives thereof. And usually, okay, yeah, so they usually have these properties. If we're going Chebyshev mode, we can think about decaying Chebyshev coefficients where they're smooth. So that's like those kind of nice hardy spaces, and exploding Chebyshev coefficients where they're in directions of contraction. So we could guess at something like, if we wanted to sort of make a guess at what this map here, like what Banach space it might be easy to work with in terms of approximation, we could write it like this. So it's like you have your coefficients, and now they've got now you're doing a Chebyshev expansion in two directions, like how you do a Fourier expansion in two directions. You now have in 2D, you now have two separate coefficients. And one of those coefficients, we want the unstable direction, we want to decay. And the stable direction, we want it, we'll allow it to blow up. It could simply decay because it's, taking its own initiative to be pleasant, but it doesn't need to. And so it looks like this. And well, if we ask, well, what are these coefficients we've done? We're just going to kind of try and mix together the, this kind of normal Chebyshev expansion with the 1 on root x squared, and then this kind of dual one, which, sorry, I'll leave that, this kind of dual one, whatever. The point is that we can sort of, we're taking Chebyshev coefficients, these kinds of coefficients, and we're writing them in terms of our functions is a sort of expansion, which may be kind of formal. For example, if we have, it could be a somewhat formal expansion, but ultimately there is an expansion there. And of course, you want to prove then that L is bounded compact and that Chebyshev approximation works. And well, I suppose that the idea is essentially that, at least, if you start with a simple case where you have independent dynamics in the x and the y direction, you have an expansion in the x and a contraction in the y, you can write your Chebyshev map here as a product of two transfer operators. So your transfer operator is a product of two transfer operators, one in the x direction, one in the y direction. And so your Chebyshev coefficients will be a product of the two Chebyshev coefficients. Now this one here is fine. We know how to compute it because it's an expanding map. This one's a bit harder, but we can sort of somehow think of it as if we sort of swap our coefficients here, we can think about, well, LH of JK is probably the same as LH inverse of KJ. Sweeping a lot of things under the carpet. And so then we can think of this transfer operator here, this nasty sort of expanding, contracting thing, as a transfer operator of a totally contracting thing with its coefficients swapped around. But this is, well, rather a totally expanding thing, and we know what to do with that. So, you know, if we're just permuting our indices here, then hopefully what it means is we can get some Frobenius norm thing and blah, blah, blah. And it all works out really well. And it also works if you can't decompose this, you do some sort of conditioning on X when you do your swap coordinates. And sorry, I'm just time reasons, I'm rushing through it. So if you actually implement this, it's quite, I mean, I implemented this in 3D, and this is not obviously not a three-dimensional picture. This is a two-dimensional slice of an eigenfunction of actually an invariant measure found using some three-dimensional system where you have one dimension of a solenoid. We have one dimension of expanding and two dimensions of contracting. So there's this y direction is contracting, which is why you see the kind of smoothness in this direction and roughness in this direction. There's going to be another one kind of coming out of the page, but I can't show you because it's not two-dimensional. It's not three-dimensional, rather. And so you can get out, for example, very good estimates of the spectrum. So this is what the spectrum of this map that I should have really written up there looks like. And I mean, all these blue points are accurate to many decimal places. So if you're ever interested in this solenoid, you can know a lot about its ergodic behavior. There's only really one thing. Well, okay. Well, I'll tell you about the orange crosses maybe, or maybe not. The other geometry, of course, most things are not squares. They're sort of funny shapes like this. That's what the sort of phase space of that linkage mechanism I showed you at the beginning was. So obviously this is not a rectangle. You can create rectangles out of this that are sort of dynamically adapted, called a Markov partition. This is an example of what you get if you look at a torus, which I suppose is easier to draw than most other things. You obviously see you take these squares and they get mapped in an appropriate way. You can actually do all this stuff with a sort of relaxed version of this, which is often nice because you don't know exactly where your stable and unstable manifolds are for the Markov partition heads in the crowd. So anyway, but one thing you do have to worry about is that you get these so-called spurious resonances, which are these orange crosses here, which really come from the fact that if you cut your interval into two, where's the guy? Okay. Okay. Yeah, because the reason for these things you get out is because you have you're sort of artificially cutting your system up into a bunch of different sets. So for example, if we do this on an interval, we have a doubling map. And well, we know that an eigenfunction of the doubling map on a non-periodic interval is 2x mod 1. That is an eigenfunction of a half, because I guess the definition of L5x is a half 5x on 2 plus a half 5x plus 1 on 2. You can convince yourself that 2x minus 1 is an eigenfunction. But if you allow jumps here, which is what you do when you divide your setup into a bunch of intervals where you're doing independent Chebyshev approximation on it, you allow these extra kinds of eigenfunctions, and that creates more resonances. So you just have to look out for that, but there's a really easy way to figure out what these guys are, because it's all about these jumps. So I suppose to summarize, you can do these kinds of exponential, so you can get these really good estimates on Anosov flows in general. They don't need to be, they're particularly nice. They don't need to have, smooth foliations, for example. They can be really sort of grotty in that sense. And in fact, that's really where these methods shine, because if you have smooth foliations, then there are sort of other smarter things you can do. But I think, people haven't really studied Holder foliations. I mean, for those who are interested in those sorts of things, partly because I think it's hard to see what they do. And this provides a very powerful way to go and look into these things and see exactly what's going on in these kinds of systems. So I think
Thanks, Caroline. Any questions? Then I may ask, when you had these two-dimensional things, so if I understood it correctly, basically, in a nutshell, one direction was more or less contracting and the other one expanding.
Yeah.
Could you also have like something like non-uniformly expanding on one thing and the other contracting or something like that, or wouldn't it be covered by your method?
It would not. Well, I mean, it depends how good a result you want. Okay, yeah, it depends how good a result you want. If you, yeah, like if you wanted it to be really good, then it wouldn't work, but you could sort of do some strange inducing thing and it would work, but that'd be a lot of work.
And yeah, Natalia.
I think about when you were talking about Anosov systems, you said the UAM method works, but you don't know why. I was curious what that means.
You. I think no one's proved that it works, and it's sort of, at least as far as I know. And you, yeah, I don't know what. Like, yeah, you see when you code it, it works, but there's not any theory there as to why. Probably some of the ideas here would show it, but.
So you talked about applying transfer operator with Chebyshev's to contractions. And I was wondering, what information do you get in terms of this spectrum and invariant measure?
You get all the spectrum. Yeah, you can get all the spectrum that you want. So you could get a picture, well, you know, something like, I mean, you could get all this stuff out and you could get exactly what the eigenfunctions, say, of the Koopman operator are, and you could get out the sort of, I suppose, the eigenfunctions of the transfer operator, but these things are weird distributions. So you get their kind of Chebyshev, low order Chebyshev coefficients.
But what would be the invariant measures for that then?
What would be the, sorry, value?
The invariant measures for, like when you have contractions, if they are continuous contractions, then it should be like, I don't know, delta measures, right?
Yeah, so you get
yeah. So that's what you get when you study the spectrum, like what?
Yes, so you get a delta function if you just had one, but there you sort of already know everything. So the interesting case is where you have a random contraction. So with some probability, you do the two different things.
Yeah, and then you get a finite combination of delta measures or something like that.
No, you get a fractal measure.
Oh, okay.
Like, you know, like a Cantor, like the Cantor measure if you use that contraction, or
okay,
you know,
because
whatever.
you are considering like infinitely many of them at once, like when you are considering the random combination also.
No, it's you only maybe have a finite number of them, but it's just you're kind of there are an infinite number of paths that you can take, right? Like through time, choosing different contractions.
Okay, thank you.
Any other maybe short question? Okay, then, well, let's thank Caroline and then have some announcements.
Yeah, so symbolic dynamics mainly concentrates on one particular class of dynamical systems, which most of you already know. It's subshifts. And so I'm going to be looking at subshifts and perturb the subshift by making more words to be forbidden, and then see how the topological entropy of these subshifts changes. And it's symbolic dynamics was usually, earlier it was used as a tool to model a large class of dynamical systems, and later including the Anosov map that was talked in the last class. And because of its independent applications and interesting properties, it was later studied as a different area. And let's see what the setup is. So I start with an alphabet A of size n, and full shift on A is defined to be all the bi-infinite sequences on A. And it's given the product topology on A to the power Z. It's a compact metric space. And we have the map, which is the left shift map, which is defined as follows. So you basically shift the digit to the left by 1. And subshift on A is all the closed, X is a subshift if it's a closed T-invariant subset of A to the power Z. So allowed words are a word, a finite word W is said to be allowed in X if W is a subword of some sequences in X, and the language is the collection of all allowed words in X. And ln of X, if ln of X denote the allowed words of length n, then the topological entropy is given by, so topological entropy is the exponential growth rate of the words of length n. Some famous examples, we start with the golden mean shift. So we have 2 symbols, and we're saying these are the sequences where no 2 ones are next to each other. In a sense, the word 1, 1 is forbidden. And you can see that this can be seen as a bi-infinite paths on some directed graph where the vertices are labeled. You can see here that 1, 1 is not allowed in this setup. And the next example is the even shift. So for an even shift, what we say is that between any 2 ones, there are only even number of zeros allowed. And again, this can also be represented by an edge labeled direct graph. And you can see between ones, there is always even number of zeros here. So I'll define a generalization of golden mean shift, which are subshifts of finite type. And X is a subshift of finite type if there is a finite collection F of words where X is given by all the sequences where words from F are forbidden. So for golden mean shift, 1, 1, F is equal to 1, 1. And I denote X to be equal to AF. And there are also other zero entropy systems that people are interested in. But for today's talk, I will only be concentrating on subshifts of finite type. And one particular example is Sturmian shift. Again, we have A to be 0, 1, and the growth of the complexity function is given by n plus 1. Let's move on to the object of today's talk. So what we're doing is we start with the subshift, and given a collection G of allowed words, I define this subshift XG, where it consists of all the sequences in X where words from G are forbidden. So I am making more words to be forbidden. If X is not a full shift, then there are already some words forbidden, and I make more words to be forbidden. And so simple example, if I was looking at the golden mean shift and make 0, 0 as G, and then XG just contains 2 points. If, for example, if G is equal to ln of X for some n, then XG is empty. If X is a minimal subshift, then also you can see that XG is an empty set. So to basically make it interesting, we want something that's non-minimal. And again, the words of length n of XG is contained in the words of length n in X, and because of which the entropy drops. And the entropy drops, and it's strictly less than the entropy of the parent system that you begin with. And we are interested in looking at this difference in entropy. So as I said before, I stick to the case where X is a subshift of finite type. So XG is also a subshift of finite type. And what are the questions that one can ask in this setup? of course, first is what kind of G makes XG non-empty. And what happens if the length of the words in G goes to infinity and things like that. Because when I'm calling it perturbation, is it very close to the parent system I start with? These are the questions that one will be interested in. But again, if the system was minimal, then it's not, because it's empty. So first question is, I'm fixing the number of words in the collection G and also length of the word. It doesn't have to be equal words of equal lengths, but without loss of generality, I can assume that they are all of equal length. And the question is, can we compare the drop for different collections G and G prime? Next is, what happens to the drop as n tends to infinity? If it goes to 0, then what's the rate of convergence? So yeah, so it has some application in ergodic theory. So what I'm looking at is, again, I start with a subshift of finite type and let mu be a t-invariant probability measure on X. Then for the given collection G, as before, of allowed words in X, we consider the whole HG, which is the union of all cylinders based at words from G. So I look at all the sequences where the words from G is at the position from 0. And this is considered to be a whole. And in the study of open dynamical system, people are interested in looking at the transformation on X minus this whole. And there are several questions one can ask in this setup. And of course, if the whole has positive measure and if the map is, for the general dynamical system, if the map is ergodic, then eventually the points do escape into the whole. And the question is like, how fast does it escape? And these are called escape rate. So what we're basically looking at is, we're looking at the measure of all the points that do not escape into the whole in the first n step, and its exponential decay rate. These are called escape rate. And the questions are like, can you compare the escape rate with respect to holes? And if the holes have the same measure, does the escape rate, is the escape rate the same, and so on. And we have proved that. So I was not interested in studying the drop in entropy, but this is what I was looking at. But then coincidentally, so we got that this escape rate is the difference of this entropy when the measure is the measure of maximal entropy, which is the Parry measure on the subshift of finite type. So that's one example. So if you're able to answer the questions that I mentioned before, in this setup, what we are answering is that given two holes, where does it go faster? That's the question we are answering. And also when I say n tends to infinity, what is happening in terms of holes is that when the length of the words goes to infinity, the size of the hole is decreasing. So we are given a nested sequence of holes that is convergent to points, and you're looking at the escape rate and what's the convergence rates of this escape rate. Again, subshift of finite types are also represented by directed graphs. So the same question can also be applied here. What are we doing? When we make some words to be forbidden, we're making some paths on these directed graphs to be forbidden and looking at its spectral radius. And for people who works in linear algebra, it's the same question. Given a matrix of 0, 1, you make some of the entries to be 0, and then what happens to the spectral radius again? Which changing the position of the entry that you're making 0, how does it change? So these are like several questions that one can ask. Yeah. So answers to those two questions. So the first question was, can we compare the drop in entropy for different collections G and G prime? And we define the Poincare recurrence time, which is the minimum n, where the iterate of HG intersects with HG. And then the conjecture is that if tau G is less than or equal to tau G prime, then the entropy drop also has the same relation. And for X being the full shift, we have an answer, but we don't have an answer for when X is not a full shift. For general subshifts of finite type, we don't have an answer. And when it was proved by Bunimovich and Yurchenko, it was very counterintuitive because all these holes have, on full shift, the measure, Parry measure is the uniform measure. So all these holes have the same measure, but yet these escape rates were different for different holes, and it only depended on the periodicity of these holes. And we generalized this result for more than one words. And next conjecture was the drop in entropy when n goes to infinity. So so the conjecture is that the drop converges to 0, and the rate of convergence is lambda to the power minus n, where ln of lambda is the entropy of X. So there is an exponential decay for this drop in entropy. So it was proved for subshift with one word forbidden by Lint in 1989. So what he did was, starting from an adjacency matrix, Hg basically is a perturbation of that matrix by a rank 1 matrix. Then he's looking at the spectral radius of these matrices, and he proved this result. And this was then later generalized by Ramsey for words of length 2. And recently, Ramsey also has some decay rate, but it's only n to the power minus 1. It doesn't have the exponential decay rate, but it's a very general case. It's a subshift where k many words can be forbidden. And again for for full shift, we have this result for k many words in G. So how are we doing that? So it's a consequence of some enumeration problem. So let me first define the enumeration problem. So what happens, what's the good thing about full shift is, when you're looking at the perturbed system, you're only counting all possible words of length n where words from G is forbidden. But when you're starting from a subshift and then looking at Xg, then what we're doing is we have to count all possible words that are already there in the subshift. But for full shift, we don't have to do that because all words are allowed there. And so we define this enumeration problem. So we start with words of length n, and the collection G, let's say, is A1 to AK. Okay, let me not assume that they have the same words, but the same thing. As I said before, you can always assume that it doesn't cause any problem to us. And I am saying, so a collection such as G is said to be reduced if AI is not a subword of AJ. And so what we're looking at is the number of words of length n that do not contain words from G as subwords. So I defined one more quantity, which is the number of words of length n that say ends with AI, but that's the only occurrence of a word from G in this word. So it's all the words of length n ends with AI, but there are no AJs anywhere else in between. Now I'll try to get a recurrence relation for this F of n and FAI of n. So how are we doing this? So I start with a word of length n, which is y, which is counted in F of n. So that means it's a word that do not contain words from G. And then I attach a symbol at the end. Now it's a word of length n plus 1. It may or may not contain words from G, but if it contains, it only occurs at the end. So what is the recurrence relation we have? Sorry, that has to be n. So we have n many choices for this X. So you have n F of n. And what we are getting is either words that do not contain words from G or the words of this type. So that's the first recurrence relation we get. And for the second set of recurrence relations, what I do is, again, I look at a word of length n that's counted in f of n. So that means it doesn't have words from G. And I attach, so I fix an A in G and I attach it at the end. Now it's a word of length n plus mod A, but this need not be counted in FA of n because we want to make sure that that's the only appearance of a forbidden word. So what we do is we look at the first appearance of a forbidden word in G in this word. So it cannot be completely inside this because Y does not have words from G. And it cannot be completely inside this because we assume that it's a reduced collection. So it has to be something like this. So what it tells us, whenever there is an overlapping of the tail of B and the head of A, we get a non-zero term there. So for this, we are required to define what this overlapping is. So I'll define what it is for now. These are called correlation of words. So when I have two words, A and B, first of length P, then I define the correlation AB to be a binary sequence, to be a binary word, which is defined as follows. So I place B under A and shift it to the right by L digit. And then I look at the overlapping parts. And if they overlap, I give it to be 1. And if they don't overlap, then it's defined to be 0. For example, you can do this. You can see that if it's shifted to the right by 2 digits, then they overlap. And we get this entry to be 1, and so on. And I can define a correlation polynomial where the coefficients are given from the correlation. So it was proved by Guibas and Orlesco that if you look at the generating functions for f of n and fai of n, using these correlation polynomials, these generating functions satisfy this set of equations. And now you can see it only depends upon the correlation of the words and n. Using that, the entropy is given by the logarithm of lambda g, where lambda g is the largest real root of this. So basically, if you have the generating function, it's the you're looking at the largest real pole of the generating function because you want to look at the radius of convergence. And so we are looking at the denominator of the function because it's a rational function. And this is what we have. So there are some things to observe here. So I was asking this question of, can we compare, given two G and G primes, how can we compare them? Now it's the question of how can we compare the correlation polynomials. So if the correlation polynomials are the same, then they have the same drop in entropy. And also it was proved that for one word case, there are, okay, so if you're only considering one word in G, then how many possibilities we have? We have n to the power n possibilities. So you expect n to the power n possibilities of values of drop in entropy. But we don't have those many correlation polynomials. This number is much lower. And so we don't get very many different values for this drop in entropy. Yeah, and so that's the results for full shift. Now we do want to extend it to the subshifts of finite type. And for that, we have similar occurrence relations for cases with subshifts of finite type as well. It is in terms of the weighted correlations. And using that, we're hopeful that this can be extended. The same exponential decay rate can be obtained for subshifts of finite type as well. So that is our next goal. And then also the question of what happens if it's like a suffix shift. And it was already done for one, when you have mod G equal to 1 for multidimensional case is also done. A similar exponential decay is proved by Roni Pavlov. And I don't work on multidimensional subshift, but that's another question. What happens when there are more words forbidden? So, so these are the questions that one can ask in the setup. And that's all I wanted to say. Thank you.
Thank you, Harita. Any questions?
Yes, I have a question when you define the whole. Can you go to the slide?
Yeah, here, right? Yeah.
There. So in the second part, you say this is the union of ZW. What is CW?
Yeah, it's the cylinder-based at W. So what you're looking at is the sequences where W attains at the position from 0.
Okay.
Yeah, yeah.
Perfect.
Questions?
You define this spectral using the matrix. So what is the relationship between the spectrum obtained here and the spectrum obtained for the measure of maximal entropy? Like for your directed graph, you define a matrix, and then you define the spectral for this measure matrix to be the eigenvalues.
Yeah, it's the same.
So they will turn out to be same.
Yeah,
and okay, so then you cannot get a measure with the weak mixing or the discrete spectrumness.
There are so we do have results not just for measure of maximal entropy, like for Markov measures also we have some kind of results on how does it, what happens when you perturb the system. So basically what happens to the escape rate when the holes are against cylinders, but the underlying measure is Markov measure. It's in fact, some work is also done for Gibbs measures and so on, things like that, yeah. Yeah.
Any more questions? Okay, then let's thank Harita again.